Tonight, we are going to witness humanity's longest journey to the edge of our solar system and into what Voyager found there, something nobody predicted. In 1977, NASA launched 2 spacecraft and gave them 5 years to live. No GPS, no modern computers, built with 1970s technology, a transmitter weaker than your bedroom nightlight, combined memory smaller than a single photo on your phone. They should be dead. They should be silent. Instead, nearly 50 years later, both are still alive, still whispering data back to Earth from 15 billion miles away, farther than any human-made object in history. But here is what most people never hear about. When the Voyager probes finally reached the edge of our solar system, everything we predicted was wrong. Not slightly wrong, massively wrong. The shape, the boundary, the temperature, all of it. They didn't find what we expected. They found 7 things nobody predicted. 7 discoveries that shattered our best scientific models. 7 findings so unexpected that even the world's top scientists were left speechless, confused, and forced to rewrite the textbooks from scratch. Stay with me, because by the end of this journey, you're going to find out what's actually waiting beyond our solar system and why it changes everything we thought we knew. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. 1977, the year we thought we understood where our solar system ended. Scientists had spent decades constructing models of the boundary, the invisible edge where the sun's influence stops and the rest of the galaxy begins. They had equations, predictions, consensus, the heliopause, they called it, a spherical bubble wrapping around our solar neighborhood, sitting roughly 90 to 100 astronomical units from the sun, about 90 times the distance between Earth and our star. Clean, symmetrical, predictable. They were wrong about almost everything. But in 1977, no one knew that yet. NASA was preparing to launch 2 spacecraft on what would become the longest-running space mission in human history, Voyager 1 and Voyager 2, 5-year missions to study Jupiter and Saturn, quick flybys, gather data, move on. The spacecraft weren't expected to last much longer than that, certainly not long enough to reach the edge of the solar system, let alone cross it, except they did both. And when they finally arrived at that boundary, decades later, billions of miles farther than anyone thought possible, every measurement they sent back contradicted the models. The distance was wrong. The shape was wrong. The transition was wrong. Even the magnetic field behaved in ways that shouldn't have been possible. This is the story of how 2 5-year missions became 50-year odysseys. How 2 spacecraft built with 1970s technology outlived their creators and rewrote the textbooks. How the edge of our solar system turned out to be nothing like we imagined. But first, why 1977? What made that year so critical that NASA had to launch right then, or lose the opportunity entirely? The answer lies in geometry. Every 176 years, something extraordinary happens in our solar system. The 4 giant outer planets, Jupiter, Saturn, Uranus, and Neptune, drift into a specific alignment. Not a perfect line, nothing so dramatic, but close enough that a spacecraft leaving Earth could visit each one in sequence, using the gravity of each planet to slingshot itself toward the next. This technique, called a gravity assist, had been tested only once before, by Mariner 10 in 1974, which used Venus to reach Mercury. But what NASA was planning in the late 1970s was far more ambitious, a grand tour of the outer solar system. 4 planets, 1 spacecraft, 12 years of flight time instead of 40. The alignment wouldn't happen again until the year 2153. The particular alignment occurs once every 175 years. The last time the outer planets lined up this way, the fastest thing on Earth was a galloping horse, and the light of the world came from candles and oil lamps. The next time it happens, no one alive today will see it. You could fit 7 human generations into that window, ancestors who would never meet. Their descendants. If NASA missed this chance, no one alive in 1977 would live to see the next one. The original plan was even grander. In 1964, a young aerospace engineer named Gary Flandreau, working at NASA's Jet Propulsion Laboratory, ran the orbital calculations and realized what was coming. He proposed sending 4 spacecraft in 2 pairs. One pair would visit Jupiter, Saturn, and Pluto. The other would fly by Jupiter, Uranus, and Neptune. Complete planetary reconnaissance of the outer solar system, all made possible by that once-in-a-lifetime alignment. NASA loved the idea. Congress did not. The projected cost, over $1 billion, killed the Grand Tour before it could begin. By the early 1970s, in the wake of Apollo's budget overruns and a struggling economy, ambitious space missions were politically toxic. The program was cancelled in 1971. But the planetary alignment didn't care about budgets. It was still coming. So NASA engineered a compromise. Instead of 4 spacecraft designed for the Grand Tour, they would build 2 simpler probes. Officially, the mission would target only Jupiter and Saturn. The spacecraft would be called Voyager 1 and Voyager 2, names chosen to replace the sterile designation Mariner Jupiter-Saturn 1977. 5-year missions, modest goals, funding secured, except the engineers at JPL built them to last far longer, and they designed Voyager 2's trajectory with a secret advantage. If, and this was a big if, Voyager 1 successfully completed its Saturn flyby, and if Voyager 2 remained operational, and if the funding could be extended, then Voyager 2 might keep going, past Saturn, onto Uranus, then Neptune. The Grand Tour could still happen, just not on paper. Voyager 2 launched first, August 20th, 1977, Cape Canaveral, Florida, a Titan IIIe rocket carrying a spacecraft the size of a small car, loaded with instruments and powered by a plutonium generator that would decay for decades. The trajectory was deliberately slower than Voyager 1's path, a longer route that would preserve the option to continue beyond Saturn. 16 days later, Voyager 1 lifted off, September 5th, 1977. Despite launching second, Voyager 1 would reach Jupiter first, following a faster, more direct path. Its mission was critical. It had to succeed at Saturn's moon Titan, the only place beyond Earth with a thick nitrogen atmosphere. If Voyager 1 failed, Voyager 2 would be diverted to study Titan instead, and the Grand Tour would die. Voyager 1 didn't fail, and so Voyager 2 kept flying. While the spacecraft climbed away from Earth, scientists were refining their models of the solar system's edge. Imagine this: the sun isn't quiet, it's violent. Every second it hurls 1.5 million tons of charged particles, protons, electrons, ionized atoms, outward into space at speeds approaching 1 million miles per hour. This flood of particles is called the solar wind, and it was first predicted by a physicist named Eugene Parker in 1958. When Parker submitted his theory to the Astrophysical Journal, the reviewers rejected it outright. One told him the idea was ridiculous, that he should go to the library and read up on the subject before wasting everyone's time with such nonsense. The editor, a man named Subramanian Chandrasekhar, overruled the reviewers. He told Parker, "I think this is absurd, but I don't want to see it killed. I will publish it." 4 years later, NASA's Mariner 2 spacecraft confirmed the solar wind's existence. Parker had been right. By the 1970s, scientists understood that this continuous wind creates a bubble around the solar system, a region where the sun's influence dominates. They called it the heliosphere, and they were confident they understood its structure. The predictions went like this. At some distance from the sun, the solar wind would slow down. It would hit the interstellar medium, the thin gas drifting between stars, and the collision would create a shock wave. This boundary was called the termination shock. Scientists predicted it would form somewhere between 75 and 90 astronomical units from the Sun. Beyond the termination shock, the solar wind would continue moving, but slower, subsonic, compressed. This region was called the Helios sheath, and scientists estimated it would be 10 to 20 astronomical units thick, a relatively narrow buffer zone. And then, finally, the heliopause, the true edge, the point where the solar wind's pressure balances exactly with the pressure of interstellar space. 90 to 100 astronomical units from the Sun, maybe 120 at most. The models showed a clean, symmetrical bubble, roughly spherical, perhaps slightly elongated in the direction the Sun was, moving through the galaxy like a teardrop. The crossing itself would be dramatic, quick. A spacecraft passing through would experience the transition in a matter of weeks, maybe months. The solar wind would vanish. The magnetic field would rotate 90 degrees or more as the spacecraft entered the galaxy's field. Cosmic rays, high-energy particles from distant stars and supernovae, would double in intensity, flooding the instruments with radiation. You would know, immediately and unmistakably, that you had left the solar system. That was the theory. Every major prediction, the distance, the shape, the thickness, the duration of crossing, the magnetic field rotation, the cosmic ray intensity, was based on decades of research, models tested and refined, mathematics that seemed sound, and every single one turned out to be wrong. 7 major discoveries, 7 ways the observations contradicted the models. Because the universe, as Voyager would demonstrate again and again, is always more complex, more interesting, and more surprising than our best theories predict. But Voyager 1 and Voyager 2 weren't just spacecraft. They were survival machines, engineered to function in an environment more hostile than any probe had ever faced. To understand how they reached the edge and what they discovered there, we first need to understand what kept them alive long enough to get there, because the technology itself is as impossible as the journey. 68 kilobytes. That's how much memory powers Voyager. Total, across 3 separate computer systems, each one smaller than the thumbnail image on your phone. 68 kilobytes is less than a single email with an attached photo. It's a fraction of what your smartwatch uses to display the time. And yet, with that impossibly tiny amount of computing power, 2 spacecraft have been navigating interstellar space for nearly 50 years. This shouldn't be possible. Picture this. 3 different types of computers, 2 of each kind, 6 machines total working in tandem, built entirely from discrete chips and components that were cutting edge in 1976. No microprocessors, no integrated circuits in the modern sense, just thousands of individual transistors wired together by hand, designed to survive in an environment no spacecraft had ever encountered. The command control system, the brain of the operation, 18-bit words, 64 instructions, addition and subtraction only, no multiplication, no division, 4,096 words of plated wire memory, non-volatile, meaning it doesn't forget when power flickers. The memory itself is physical, magnetic domains recorded on iron-nickel alloy, plated onto wires like microscopic tape recorders frozen in place. The flight data system, faster, built with CMOS chips, capable of 81,000 operations per second, which sounds impressive until you realize a modern iPhone performs roughly 200 billion floating point operations per second. Voyager's computer is more than 2 million times slower than the phone in your pocket, and yet it works. It's still working. The computers process 8,000 instructions per second. Your phone, 14 billion. The entire computational power of both Voyager spacecraft combined is less than what runs a single frame of animation on a streaming service. But here's what your phone can't do: operate continuously for 48, Years in the vacuum of deep space, bombarded by cosmic radiation, experiencing temperature swings of hundreds of degrees with no possibility of repair, receiving commands that take nearly a full day to arrive, and sending back data so faint it arrives at Earth weaker than the battery in a digital watch. The spacecraft runs on nuclear decay. 3 radioisotope thermoelectric generators, RTGs, mounted on a boom extending away from the main body. Inside each one, 24 pressed spheres of plutonium-238 dioxide, encased in iridium, glowing red-hot from their own radioactive decay. The heat differential between the plutonium and the cold of space drives thermocouples, no moving parts, just physics, converting thermal energy directly into electricity. At launch in 1977, the 3 RTGs produced 470 watts, enough to power a few light bulbs. By 2024, that number had dropped to around 220 watts, half the original power. Gone. Not because the plutonium ran out, it has an 87.7-year half-life, but because the thermocouples themselves degraded over time. The materials aged, the efficiency dropped, and every year, Voyager loses another 4 watts, the equivalent of 1 dim LED bulb per year, vanishing into entropy. NASA has been shutting down instruments one by one, heaters, backup systems, scientific tools that completed their missions decades ago. In 2025, they turned off Voyager 1's cosmic ray subsystem, the instrument that had confirmed the spacecraft crossed into interstellar space. In 2026, more will follow. The engineers estimate that by the early 2030s, there won't be enough power left to run even a single science instrument. The spacecraft will fall silent, not because they broke, but because the universe is patient and decay is inevitable. Right now, this moment, Voyager 1 is transmitting a 23-watt radio signal, weaker than the LED bulb in your bedroom, weaker than a refrigerator light, beamed toward Earth from over 15 billion miles away. By the time that signal reaches us, it has spread across space, diluted by distance, reduced to less than 1/billionth of a watt. A few hundred attawatts, that is less than 1/quintillionth of the power used by a common TV remote. For reference, a good FM radio receiver can detect signals 1,000 times stronger. Voyager's transmission is arriving at Earth more than 1,000 times fainter than what your car radio considers too weak to hear, and yet we hear it. The Deep Space Network, 3 massive antenna complexes positioned around Earth, spaced 120 degrees apart, so at least one can always see Voyager, listens. 70-meter dishes in California, Spain, and Australia, trained on a point in space so distant that light itself takes 23 hours to cross the gap. 23 hours? You send a command, you wait. Nearly a full day later, Voyager receives it. Voyager responds. Nearly another full day passes. Then, if everything worked, the reply arrives. 2 days for a conversation, and in that signal travelling at the speed of light across a distance so vast it defies human comprehension, is data. Science. Measurements of magnetic fields and plasma waves and cosmic rays in a region of space no human eyes will ever see. All transmitted at 160 bits per second. Your home Wi-Fi? Billions of bits per second. Voyager's data rate is 7 million times slower. Sending a single smartphone photo would take hours, but it's enough. In 2010, a single bit flipped in Voyager's memory. 10 became a 1, just 1 bit, the smallest unit of information possible. But that single corrupted bit caused the spacecraft's computers to lose synchronization. Commands started executing 2.5 hours late. NASA wrote a software, patch, transmitted it across billions of miles. Flip the bit back. Problem solved. In 2022, Voyager 1's attitude control system, the computer responsible for keeping the antenna pointed at Earth began sending garbled telemetry. The spacecraft was functioning normally, but the data made no sense. Engineers traced the problem to the computer routing information through a system that had been offline for years. They wrote another patch, sent it up, over 18 hours each way, rerouted the data flow, fixed. In 2023, memory corruption struck again, this time more severe. For 5 months, Voyager 1 stopped transmitting readable data entirely. Engineers spent weeks analyzing the corrupted signal, identified a single failed memory chip in the flight data system, rewrote portions of the flight software, split the affected code into pieces because no single location had enough free memory to hold it all, uploaded the fragments one by one and reassembled them on a spacecraft, built when the Apple II hadn't been invented yet. It worked. Voyager resumed transmissions. Think about what that means. Engineers on Earth, using computers millions of times more powerful than Voyager's, sending instructions to a machine moving through interstellar space at 38,000 miles per hour, debugging 50-year-old code written in assembly language by people who are now retired or dead, updating software across a gap so vast that confirmation of success takes 2 full days to arrive. And it works. The engineers who designed Voyager in the early 1970s didn't have desktop computers. They had slide rules, mechanical calculators, drafting tables. Everything, the trajectory calculations, the power budgets, the thermal analysis, the communications link margins, was done by hand, checked by hand, verified by committees of humans with pencils and paper. The Voyager team designed a spacecraft to last 5 years, knowing it would be exposed to radiation, temperature extremes, micrometeorite impacts, and the bone-deep cold of deep space with no maintenance, no spare parts, no possibility of retrieval. And they overbuilt it, not by accident, by philosophy. Every system had a backup. Every computer had a twin. The thrusters were tested to 500,000 firings, enough to reach Saturn, the farthest planned destination. By the time Voyager 2's low-energy charge particle instrument was finally shut down in 2025, that instrument's stepper motor had completed over 8.5 million steps, 17 times its design life. The engineers didn't know Voyager would reach interstellar space. They didn't plan for it, but they built something resilient enough that when the opportunity came, when the spacecraft kept working long after their warranties expired, the mission could continue. 50 years later, the hardware is still operational, the plutonium is still decaying, the computers are still computing, the signal is still transmitting. Because in 1976, a team of engineers with slide rules and an impossible deadline built 2 machines that refused to die. But survival was never the goal. Discovery was. And what Voyager discovered at the edge contradicted every model, every prediction, every assumption scientists had built over decades of research. The first shock came in 2004, when Voyager 1 crossed a boundary that wasn't supposed to be there, at a distance that was impossible. Discovery number 1. The prediction was wrong, not by a few miles, not by a rounding error, by 2.4 billion miles. That is how far the true edge of our solar system was from where the textbook said it should be. But the first sign of that massive discrepancy came on December 16, 2004. Voyager 1, 94 astronomical units from the Sun, already farther than the termination shock was supposed to be, detected something impossible. The solar wind, which had been screaming outward at 400 kilometers per second for 27 years, suddenly slowed, dramatically. The spacecraft's instruments registered the change within hours. Particle counts spiked, magnetic field strength doubled. Voyager had crossed the termination shock, except it wasn't supposed to be there yet. Scientists had predicted the shock would form somewhere between 75 and 90 astronomical units from the Sun. Voyager 1 hit it at 94, 4 astronomical units beyond the upper prediction. 372 million miles farther than the model said was possible, and that was only the beginning. But here's where it got strange. The termination shock wasn't a fixed wall. It moved, like a living thing breathing in and out, expanding and contracting across billions of miles of space as the pressure from the solar wind rose and fell. Voyager 1 had been crossing and recrossing the shock since August 2002, not once, multiple times. The spacecraft would detect the characteristic signatures: compressed magnetic fields, slowed particles, increased radiation. Then days or weeks later, the shock would retreat back past Voyager's position, and the spacecraft would find itself back in the supersonic solar wind. August 2002, August 2003, August 2004. Each time, the instruments recorded the crossing. Each time, mission scientists wondered if this was the final crossing. Each time, the shock moved again. The boundary was dynamic, oscillating, moving inward and outward across several astronomical units over the course of weeks or months, driven by variations in solar wind pressure millions of miles behind it. This wasn't in the models. The predictions had described a clean transition. A spacecraft would cross once, maybe experience some turbulence for a few days or weeks, and then settle into the helios sheath, the region between the termination shock and the true edge of the solar system. Instead, Voyager 1 spent 2 years ping-ponging back and forth across a boundary that refused to stay still. August 30th, 2007. Voyager 2 crossed the termination shock at 84 astronomical units. 10 astronomical units closer to the Sun than Voyager 1. Think about what that means. The two spacecraft traveling in different directions. Voyager 1 heading north above the plane of the solar system. Voyager 2 heading south encountered the same boundary at radically different distances, 930 million miles apart. The termination shock wasn't spherical, it wasn't even symmetrical. The solar system's protective bubble, the heliosphere, was being compressed on one side and stretched on the other, like a balloon pressed against a wall. The interstellar magnetic field was pushing harder against the southern hemisphere of the solar system, squeezing the termination shock inward in that direction. This was the first direct proof that every assumption about the shape of the heliosphere was wrong. Scientists had known, theoretically, that the heliosphere might be elongated. The Sun moves through the galaxy at nearly 500,000 miles per hour, and that motion should compress the bubble in front and stretch it into a tail behind, like the shape of a comet. But no one expected the termination shock to be asymmetrical from north to south. No model had predicted a 10 astronomical unit difference, and Voyager 2's crossing was violent. The spacecraft detected at least 5 separate shock crossings over the course of just 2 days. The termination shock moved back and forth, oscillating across Voyager's position as solar wind pressure waves, launched by storms on the Sun years earlier, slammed into the boundary from behind, pushing it outward, then letting it collapse back inward. Each crossing lasted minutes to hours. Between them, Voyager 2 found itself alternately in the supersonic solar wind and the subsonic helios sheath, the instruments recording wild swings in particle energies and magnetic field strength. It was chaos. After the final crossing, both Voyagers entered the helios sheath. The region scientists had predicted would be 10 to 20 astronomical units thick. They were in for another surprise. The helios sheath turned out to be far thicker than expected. And stranger. The solar wind, which should have been subsonic, slower than the speed of sound in the surrounding plasma, was still moving fast. Not as fast as before the shock, but faster than the models predicted. Much of the solar wind's kinetic energy was being transferred not to heat as expected, but to charged particles. Pickup ions, cosmic rays. The temperature was wrong too. Scientists expected the helios sheath plasma to be over 1 million degrees Kelvin. Voyager 2's instruments measured 100,000 to 200,000 Kelvin, 5 to 10 times cooler than predicted. The energy had to go somewhere, and it did, into accelerating particles to near relativistic speeds. The Helios sheath wasn't a quiet transition zone, it was an acceleration chamber. 2010, Voyager 1, now deep in the Helios sheath, detected cosmic rays increasing earlier than expected. Galactic cosmic rays, particles from distant stars and supernovae streaming through interstellar space, should have been blocked by the heliosphere, but they were getting in. The intensity was rising. Something had changed. June 2012. Voyager 1's instruments detected a phenomenon no one had anticipated, a structure scientists would later call the magnetic highway. Magnetic field lines from the Sun, which normally spiral outward in all directions, were suddenly perfectly aligned, running parallel to each other, and particles, both solar particles and galactic cosmic rays, were flowing in both directions along these field lines, some streaming outward from the Sun, others streaming inward from interstellar space. It was a highway, a conduit, solar magnetic field lines connecting directly to the galactic magnetic field, allowing particles to pass freely between the heliosphere and interstellar space. This structure had never appeared in any scientific model. No one predicted it. No one expected it. The magnetic highway existed in a region that was supposed to be chaotic, turbulent, magnetically disconnected from the outside universe. But there it was. August 25th, 2012, Voyager 1's instruments registered a sudden, sharp drop in solar particles. Within hours, the count fell to nearly zero. At the same time, galactic cosmic rays spiked. The spacecraft had been detecting increasing cosmic ray intensity for years, but this was different. This was a step change, an abrupt transition. Voyager had crossed something. But what? The magnetic field didn't rotate. That was the problem. Every model, every prediction, every theoretical paper published over the previous 30 years said the same thing. When a spacecraft crosses the heliopause, the true boundary between the solar system and interstellar space, the magnetic field should rotate dramatically. The Sun's magnetic field points in one direction, the galaxy's field points in another. The transition should be obvious. Voyager 1's magnetometer detected no rotation at all, so scientists hesitated. They analysed the data, they debated, they ran simulations, they compared measurements. For a year, the question remained open. Had Voyager 1 left the solar system, or had it entered some new, unknown region that fit no existing model? The problem was simple. Voyager 1's plasma instrument, the one tool that could directly measure the density and composition of the surrounding plasma, confirming whether it was solar or interstellar, had failed in 1980. So scientists had to use indirect methods. They waited for plasma waves. Shock waves launched by solar storms travelling outward through space excite oscillations in the surrounding plasma. Those oscillations have a specific frequency, and that frequency depends on electron density. If you can measure the frequency, you can calculate the density. And if the density matches what's expected in interstellar space, you have your answer. Between October 2012 and April 2013, Voyager 1 detected multiple plasma wave events. Each one allowed scientists to calculate the electron density. Each measurement came back consistent with interstellar plasma, not solar wind, interstellar medium. But the magnetic field still hadn't rotated. How do you reconcile that? September 12, 2013. NASA made it official. Voyager 1 had crossed the heliopause on August 25, 2012, at a distance of 121 astronomical units from the Sun, nearly 2.4 billion miles beyond the original predictions. The heliopause was supposed to form around 90 to 100 astronomical units. Voyager found it at 121. The Helios sheath, predicted to be 10 to 20 astronomical units thick, turned out to be 27 astronomical units thick from Voyager 1's entry point to exit. And the magnetic field? The explanation was almost embarrassing in its simplicity. Pure coincidence. The sun's magnetic field at that location, at that moment, happened to be aligned with the galaxy's magnetic field. Same direction, same orientation. So when Voyager crossed from one to the other, there was no rotation to detect. If Voyager 1 had crossed the heliopause a few years earlier or later, or at a different location, the field would have rotated as predicted. But it didn't, because the universe doesn't perform on command. Voyager 2 would get the chance to check. November 5th, 2018. Voyager 2 crossed the heliopause at 119 astronomical units. Its magnetometer detected a 20-degree shift in the angle of the magnetic field. Not the massive 90-degree rotation the textbooks predicted, just 20. And with that single measurement, scientists realized the heliosphere's shape was even stranger than the termination shock symmetry suggested. The sun's protective bubble wasn't a bubble at all. Discovery number 2. For decades, scientists drew the same picture. A sphere, maybe elongated, maybe stretched into a tail by the sun's motion through space, but fundamentally spherical, symmetrical, predictable. The kind of shape you could model with equations that fit comfortably on a page. The heliosphere, our sun's magnetic bubble, the protective shield separating us from the raw violence of interstellar space, was supposed to be simple, clean, understandable. Voyager proved them wrong. November 5th, 2018. Voyager 2's magnetometer registered a shift in the magnetic field of only about 20 degrees as it crossed the heliopause. 20 degrees. Not the 90-degree rotation most models predicted. Not even close. The field inside the sun's bubble and the field outside in the galaxy were almost perfectly aligned, a result that left scientists stunned for the second time in a decade. But that wasn't the disturbing part. The disturbing part was what that measurement implied. Voyager 1 had crossed the heliopause at 121 astronomical units. Voyager 2 crossed at 119, just 2 astronomical units apart. The spacecraft were traveling in completely different directions, one heading north above the plane of the solar system, the other heading south below it. Yet they encountered the same boundary at nearly identical distances from the sun. If the heliosphere was spherical, that would make sense. A sphere extends the same distance in all directions, but Voyager 1 and Voyager 2 had already shown the heliosphere wasn't spherical. The termination shock was 10 astronomical units closer on the south side than the north. The bubble was squashed, asymmetrical. So how could both spacecraft cross the heliopause at almost the same distance? The answer rewrote the shape we thought we knew. The heliosphere isn't a bubble, it's a bullet, or a teardrop, or something between the two, compressed in front, flattened on the sides, stretched into a long tail behind. Picture this: the sun, dragging its magnetic field and solar wind along with it, moves through the galaxy at over 200 kilometers per second, 500,000 miles per hour. That's fast enough to circle the Earth's equator in less than 3 minutes. But relative to the local interstellar medium, the thin gas and dust filling the space between stars, the sun moves much slower, about 23 kilometers per second, 52,000 miles per hour. Slower than expected, but still fast enough to distort everything. As the sun plows forward through the interstellar medium, the heliosphere compresses in the direction of motion. The nose, the front edge, gets pushed inward, the sides flatten, and behind the sun, in the wake of its passage, the heliosphere stretches into a tail. Not a short tail, not a modest extension, a tail that may extend hundreds, possibly thousands, of astronomical units into space. The shape isn't symmetrical, it never was. The traditional image, a neat sphere with a comet-like tail, was wrong from the beginning. Both Voyagers crossed near the nose, the compressed front edge, the place where the heliosphere is thinnest, where the boundary comes closest to the sun. That's why both spacecraft encountered the heliopause at similar distances, despite travelling in different directions. They weren't measuring the heliosphere's width, they were measuring its compressed thickness at the front. And that thickness, about 120 astronomical units, 11 billion miles, far beyond predictions, but also far less than the heliosphere's true extent in other directions. But there was supposed to be another boundary. For 25 years, scientists predicted that ahead of the heliosphere, in the direction of the sun's motion through the galaxy, there should be a bow shock. The same kind of shock wave that forms in front of a supersonic jet. The same physics that creates a sonic boom. The sun, moving through the interstellar medium, should push a wave of compressed plasma ahead of it, where that wave transitions from supersonic to subsonic speeds. A shock should form, sharp, discontinuous, detectable. Scientists calculated where it should be, around 230 astronomical units from the sun, more than twice the distance to the heliopause. Except it's not there. 2012. NASA's Interstellar Boundary Explorer, IBEX, a spacecraft designed to image the heliosphere from Earth orbit by detecting energetic neutral atoms bouncing back from its boundaries, measured something unexpected. The sun's speed through the local interstellar cloud was slower than previous estimates, 23.2 kilometers per second instead of 26.3, 7,000 miles per hour slower. That difference, small in cosmic terms, changed everything. Combined with new measurements showing the interstellar magnetic field was stronger than expected, the slower speed meant the sun wasn't moving fast enough to create a bow shock. The pressure wasn't sufficient. The interaction wasn't violent enough. Instead of a shock, there's a bow wave. Gentler, more like the ripple created by a boat moving through water than the explosive discontinuity of a jet breaking the sound barrier. The boundary scientists expected to find at 230 astronomical units simply doesn't exist. But if you ask different scientists what shape the heliosphere actually has, you'll get different answers. Stamatios Krimigis and his team at Johns Hopkins University analysed data from both Voyagers and the Cassini spacecraft, which detected energetic neutral atoms while orbiting Saturn. Their conclusion: the heliosphere is more bubble-shaped than comet-shaped, nearly spherical. The interstellar magnetic field is strong enough to squeeze the heliosphere from all sides, preventing a long tail from forming. The bubble expands and contracts with the solar cycle, but maintains a roughly symmetric shape. For 60 years we've had the wrong image, Krimigis said. The heliosphere is round, absolutely round, except Nathan Schwadron at the University of New Hampshire disagrees. He argues the energetic neutral atoms Cassini detected don't necessarily come from the heliopause. They could originate from plasma changes inside the heliosphere itself, varying with the solar cycle. The data, he says, tells us nothing about the heliosphere's overall shape. The traditional comet model, compressed nose, long tail, remains the best explanation. And then there's Merav Ofer at Boston University. Her models, incorporating the behavior of pickup ions, interstellar atoms that get ionized and swept up by the solar wind, suggest something stranger: a croissant shape, two lobes curling away from a central bulge. No long tail. The pickup ions, she argues, dominate the thermodynamics near the termination shock, creating a spherical structure. But beyond the shock, where the ions escape, the heliosphere deflates, collapsing into a flattened, folded shape unlike anything previously imagined. 3 teams, 3 interpretations, 3 fundamentally different shapes, all based on the same data. You might wonder why the shape matters. Because the shape determines how cosmic rays enter the solar system. Galactic cosmic rays, high-energy particles accelerated by distant supernovae, streaming through the galaxy at nearly the speed of light, are lethal. A human exposed to deep space radiation for extended periods faces catastrophic cellular damage. DNA breaks down, cancer risk skyrockets, nervous system degradation accelerates. The heliosphere shields us, deflects some of those particles, slows others. but the level of protection depends on direction. If you're traveling toward the nose of the heliosphere, where the boundary is compressed, where the magnetic field lines are tangled and turbulent, cosmic rays have a harder time penetrating. The shield is thick, the protection is strong. But if you're traveling toward the tail, if that tail exists, where the heliosphere stretches thin, where the magnetic field lines open and connect directly to interstellar space, cosmic rays flow in more easily. The shield weakens, the protection fails. For future missions beyond the heliopause, for spacecraft traveling to other stars, for any human who ventures into interstellar space, the shape of the heliosphere determines which direction is survivable, and we still don't know what that shape is. The Sun isn't stationary in the galaxy. It's traveling through a region called the local interstellar cloud, a wisp of gas and dust about 30 light-years across, one of many such clouds scattered through the Milky Way. The Sun entered this cloud somewhere between 44,000 and 150,000 years ago. At some point in the future, maybe a few thousand years, maybe hundreds of thousands, it will exit the other side and enter a different region of the galaxy with different density, different pressure, different magnetic field strength. When that happens, the heliosphere will change. It might compress further, shrinking the protective bubble inward toward the inner solar system. It might expand, pushing the heliopause farther out. The shape might shift. The tail might lengthen or disappear. The nose might flatten or round out. The heliosphere is not a fixed structure. It's dynamic, responsive, constantly reacting to the environment through which the Sun moves. What Voyager measured, what both spacecraft crossed in 2012 and 2018, was a snapshot, a single moment in a process that unfolds over millennia. The boundary we discovered is already changing, but understanding the shape was only half the problem. Scientists still had to understand the crossing itself. When Voyager 1 approached the heliopause in 2010, mission teams expected a clean transition, a few weeks, maybe a few months of turbulence, then a clear passage into interstellar space. Instead, what they witnessed was something far stranger. The crossing didn't take weeks. It took years, and when it finally happened, the boundary refused to stay still. Discovery number 3. 2010, Voyager 1, still deep in the heliosheath, detected something strange. The solar wind, the outward flow of particles that had been screaming away from the Sun at hundreds of kilometers per second for the spacecraft's entire journey, slowed. Not gradually, abruptly. Within months, the radial velocity dropped to nearly zero. Voyager had entered what scientists would later call the stagnation region, a place where the solar wind's outward motion simply stopped. The particles weren't disappearing. They were piling up, turning sideways, deflected by the pressure of the interstellar medium pressing inward from the other side of the heliopause. This was 113 astronomical units from the Sun, 10.5 billion miles, and scientists began to suspect that after 33 years of travel, Voyager was finally approaching the edge. But they expected a clean crossing. Weeks, maybe a few months of turbulence, then a clear passage into interstellar space. Instead, what followed was 2 years of confusion. December 11th, 2011. NASA announced that Voyager 1 had entered a new region they called cosmic purgatory. Not inside, not outside, somewhere in between. Charged particles streaming from the Sun slowed even further. The Sun's magnetic field doubled in strength, compressed by the pressure from interstellar space pushing back. Particles from inside the heliosphere declined by nearly half. High-energy electrons from outside increased 100-fold. The boundary was close. Everyone knew it. But where? June 2012. Voyager's instruments registered another change. Something no model had predicted. Something that shouldn't exist. The magnetic field lines, which normally spiral outward from the Sun in all directions, twisted and tangled by the solar wind's rotation, suddenly aligned. Perfectly. running parallel to each other, straight, organized, and particles were flowing in both directions along these field lines. Solar particles streaming outward, galactic cosmic rays flowing inward. Ed Stone, Voyager's project scientist, described it in December 2012. Voyager has discovered a new region of the heliosphere that we had not realized was there. We're still inside, apparently, but the magnetic field now is connected to the outside, so it's like a highway letting particles in and out. A magnetic highway. The magnetic field in this region was 10 times more intense than anything Voyager had encountered before the termination shock. It was expected to be the last barrier before the spacecraft exited the solar system completely. But this structure, this perfectly aligned corridor of magnetic field lines connecting the inside of the heliosphere directly to interstellar space, had never appeared in any scientific model. No one anticipated it. No one predicted it. No theoretical framework suggested it should exist. Yet there it was. August 25th, 2012, day 238 of the year. Voyager 1's instruments recorded a sharp, sudden drop in solar particles. Within hours, the count fell to nearly zero. At the same time, galactic cosmic rays spiked. The intensity jumped. The spacecraft had been detecting increasing cosmic ray levels for years, but this was different. This was a step change, an abrupt transition. Something had happened, except no one knew what. The problem was simple and maddening. Every model, every prediction, every theoretical paper published over the previous 30 years said the same thing. When a spacecraft crosses the heliopause, the true boundary between the solar system and interstellar space, the magnetic field should rotate dramatically. The Sun's magnetic field points in one direction. The galaxy's field points in another. The transition should be obvious, measurable, undeniable. Voyager 1's magnetometer detected no rotation at all. The magnetic field stayed, almost solar-like. No change in angle, no shift in direction. So what had the spacecraft crossed? Scientists examined the data. They ran simulations. They compared measurements. They debated. Voyager 1's plasma instrument, the one tool that could directly measure the density and composition of the surrounding plasma, confirming whether it was solar or interstellar, had failed in 1980, 32 years earlier, long before this moment. So they had to use indirect methods. They waited for plasma waves, for oscillations triggered by solar storms. When shock waves from the sun slam into plasma, they excite oscillations, vibrations with a specific frequency that depends on electron density. Measure the frequency, calculate the density. If the density matches interstellar space, you have your answer. October 23 through November 27, 2012. Voyager's plasma wave instrument detected faint oscillations, low frequency, brief. April 9th, 2013. Stronger oscillations, clearer, higher frequency. The plasma around the spacecraft was vibrating like a violin string, excited by a coronal mass ejection that had erupted from the Sun in March 2012, 13 months earlier. Scientists at the University of Iowa analyzed the frequencies. The electron density came back, 0.08 particles per cubic centimeter, 80 times higher than the heliosheath. Exactly what was expected in the interstellar medium, but the magnetic field still hadn't rotated. How do you reconcile that? September 12th, 2013. NASA made it official. Voyager 1 had crossed the heliopause on August 25th, 2012, at a distance of 121.6 astronomical units from the Sun. The heliopause was supposed to form around 90 to 100 astronomical units. Voyager found it at 121.6. The heliosheath, predicted to be 10 to 20 astronomical units thick, turned out to be 27.6 astronomical units thick from Voyager's entry point to exit. And the magnetic field? The explanation was almost embarrassing in its simplicity. Coincidence. Pure astronomical coincidence. The sun's magnetic field, at that location, at that moment, happened to be aligned with the galaxy's magnetic field. Same direction, same orientation. So when Voyager crossed from one to the other, there was no rotation to detect. If Voyager 1 had crossed the heliopause a few years earlier or later, or at a different location, the field would have rotated as predicted. But the universe doesn't perform on command. The spacecraft happened to cross at precisely the spot and time where both fields aligned. Scientists confirmed this years later when they compared Voyager's magnetic field measurements with data from the Interstellar Boundary Explorer, IBEX, which had mapped the ribbon of energetic neutral atoms surrounding the heliosphere. The ribbon's center marked the direction of the pristine interstellar magnetic field, and Voyager 1, traveling north of the ecliptic plane, crossed at a location where the solar and interstellar fields happened to share the same orientation. November 5th, 2018. Voyager 2 crossed the heliopause at 119 astronomical units. Its magnetometer detected a rotation in the magnetic field, but not 90 degrees as many models predicted, just 20 degrees. A small shift within the range of normal fluctuations, and the crossing itself was radically different. Voyager 1 had taken about 28 days to fully cross the heliopause, dipping in and out multiple times as the boundary moved. Scientists counted 5 separate crossings between days, 210 and 238 of 2012, as Voyager ping-ponged back and forth across a shifting, breathing boundary. Voyager 2 crossed in less than 1 day, clean, sharp, definitive. On November 5th, the spacecraft registered a sudden decrease in solar wind particles and a simultaneous increase in galactic cosmic rays. No precursor events, no magnetic highway, no prolonged approach, just a crossing. Why the difference? Location, solar activity. Timing, Voyager 1 crossed during a period of low solar activity, when the heliosphere was compressed and the boundary was less stable. Voyager 2 crossed during a different phase of the solar cycle, when conditions were calmer but the structure simpler. And Voyager 2 crossed in the southern hemisphere, while Voyager 1 crossed in the north. Different parts of the heliosphere, different magnetic field configurations, different encounters with the same boundary. The heliopause isn't uniform, it's not a smooth shell. It's asymmetric, dynamic, and location-dependent. The heliopause doesn't stay still. It expands, it contracts, it breathes, like a lung responding to changes in solar wind pressure from behind and interstellar pressure from ahead. When solar activity increases, the solar wind strengthens. The pressure rises. The heliopause pushes outward, expanding the bubble by several astronomical units over weeks or months. When solar activity declines, the pressure drops. The interstellar medium pushes back. The heliopause contracts inward. This is why Voyager 1 crossed multiple times in 2012. The boundary wasn't fixed, it was moving. Back and forth across the spacecraft's position, driven by pressure waves launched by solar storms millions of miles behind. Scientists expected the heliopause to be dynamic, but they didn't expect it to move this much, this fast, across such large distances. Picture this: a boundary 10 billion miles from Earth, oscillating inward and outward by hundreds of millions of miles, several astronomical units, over the course of weeks. Not because of anything happening locally, but because of storms on the Sun that occurred months or years earlier there, pressure waves rippling outward through the heliosphere, compressing and releasing the heliopause like a drumhead responding to distant thunder. Even after Voyager 1 crossed in August 2012, the boundary continued to move. The spacecraft remained close enough to the heliopause that changes in solar wind pressure could still affect the environment around it. For months afterward, Voyager detected oscillations, fluctuations in particle counts and magnetic field strength, as the boundary breathed in and out just behind the spacecraft's position. The crossing wasn't a moment, it was a process, a transition zone, a region where the influence of the Sun and the influence of the galaxy overlap, compete, and shift. But crossing the heliopause was only half the discovery. The other half was what Voyager found on the other side. For the first time in human history, a spacecraft was directly sampling the interstellar medium, the material that fills the space between stars. And every measurement revealed that the textbooks had gotten the details wrong. Discovery number 4. Interstellar space was supposed to be cold, empty, quiet, a near-perfect vacuum, essentially featureless. The textbooks described it that way. Models predicted it. Astronomers observed distant stars through it and made assumptions about its properties based on how starlight bent and scattered. But no spacecraft had ever measured it directly. Not from the inside, not from within the medium itself, until Voyager crossed the heliopause, and every measurement the spacecraft returned revealed that the textbooks had gotten the details wrong. For the first time in human history, a spacecraft was directly sampling the interstellar medium, the material that fills the space between stars, not observing it from 11 billion miles away, not inferring its properties from absorption lines in stellar spectra, actually there, inside it, measuring it. Voyager 1 became humanity's first probe of the very local interstellar medium in August 2012. But the spacecraft's plasma instrument had failed in 1980, 32 years earlier. So scientists had to rely on indirect methods, plasma oscillations excited by shock waves from the Sun, to determine the density of the surrounding medium. The first measurement came in October through November 2012. A coronal mass ejection that had erupted from the Sun earlier that year finally reached Voyager's position, exciting electrons in the plasma around the spacecraft. Those electrons oscillated at a specific frequency, 2.6 kHz, and the frequency of plasma oscillations depends directly on electron density. Scientists at the University of Iowa calculated the density from that frequency, 0.08 electrons per cubic centimeter. The prediction, based on decades of theoretical models and remote observations, had been between 0.05 and 0.22 electrons per cubic centimeter. Voyager's measurement fell within that range, but barely, and as the spacecraft continued traveling deeper into interstellar space, more measurements revealed something unexpected. The density wasn't constant, it varied, 10 to 20% over distances of just a few astronomical units, tens of millions of miles. The interstellar medium, even in this relatively quiet region near the Sun, was clumpy, turbulent, not the smooth, uniform sea that models had assumed. Plasma oscillations appeared again in April through May 2013, stronger this time, higher frequency. The electron density had increased to 0.083 particles per cubic centimeter. The interstellar medium was getting denser as Voyager traveled away from the heliopause. Voyager 2, with its working plasma instrument, provided even more precise measurements when it crossed the heliopause in November 2018. The first electron density it measured, 0.039 particles per cubic centimeter. By June 2019, that figure had jumped to 0.12 particles per cubic centimeter. The density was increasing as both spacecraft moved farther from the boundary. Not decreasing, not staying constant. Increasing. Scientists aren't certain why. One theory suggests that interstellar magnetic field lines near the heliopause might be stronger, drawing particles away from the affected area. Another theory proposes that particles pushed along by the interstellar wind slow down when they approach the heliosphere, like traffic slowing near an obstruction, causing a density traffic jam just beyond the heliopause. But here's what matters. These were real measurements, direct samples, not theoretical predictions, and they didn't match what the models had assumed. The density measurements were surprising. The temperature measurements were disturbing. When Voyager 2 crossed the heliopause, its plasma instrument measured the temperature of the interstellar medium directly. The result, between 30,000 and 50,000 Kelvin, 54,000 to 90,000 degrees Fahrenheit. Models and remote observations had predicted the very local interstellar medium's temperature would be between 15,000 and 30,000 Kelvin. Voyager measured temperatures almost twice as high. But here's the paradox that makes the measurement even stranger. You would freeze. Picture this. If you could somehow survive in interstellar space without a spacesuit, ignoring the radiation, the vacuum, everything except temperature, you would freeze to death, not burn. Because temperature, in this context, describes the kinetic energy of individual particles, how fast they're moving, and in the interstellar medium, those particles are moving very fast, fast enough to register as 90,000 degrees Fahrenheit. But there are so few of them, 0.08 particles per cubic centimetre, that they can't transfer heat to anything. Temperature, as we understand it on Earth, requires density. It requires enough particles colliding with your skin to actually transfer thermal energy. In the interstellar medium, the particles are scattered so thinly that even though each individual particle is scorching hot, there aren't enough of them to warm you. The spacecraft itself experienced this directly. Voyager's instruments measured the plasma temperature at tens of thousands of degrees, yet the spacecraft remained cold. No thermal damage, no overheating. The environment couldn't transfer heat because there was almost nothing there to transfer it. This is what emptiness looks like when measured directly. Hot particles. Almost no particles. A contradiction that only makes sense when you stop thinking about temperature the way we experience it on Earth. On Earth, at sea level, a cubic centimetre of air contains 30 quintillion molecules. That's a 3 followed by 19 zeros. In the interstellar medium, a cubic centimetre contains 0.08 particles, not quintillions, less than 1. Imagine taking all the air in a room, a small bedroom, maybe 10 feet by 10 feet, and spreading it out across the entire volume of Earth's atmosphere. That's roughly the difference in density between Earth's air and the space Voyager is travelling through, but calling it a vacuum doesn't quite capture what it is, because it's not empty. It's plasma, ionized hydrogen and helium, remnants of the Big Bang, mixed with heavier elements forged in the cores of stars and blown into space by supernovae. It has structure, it has pressure, it has magnetic fields threading through it. It vibrates with waves launched by stellar explosions that occurred thousands of years ago. The pressure in the interstellar medium is 1/10 trillionth of Earth's atmospheric pressure at sea level. That's 10 to the negative 17th torr, for those keeping track. Compare that to the best vacuum laboratories on Earth, which can achieve pressures down to about 10 to the negative 12th torr, 100,000 times higher than interstellar space. Interstellar space is a better vacuum than anything we can artificially create, yet it's not nothing. Voyager's magnetometer measured the magnetic field strength at around 0.4 nanotesla in the regions just beyond the heliopause, about 1/1,000,000th the strength of Earth's magnetic field. Weak, but present. And that field carries information. It connects to the galaxy's larger magnetic structure. It guides cosmic rays. It shapes how charged particles move through space. Even the emptiest parts of the universe still contain threads of structure invisible to us, but measurable by instruments sensitive enough to detect them. None of these measurements were dramatically wrong. The density fell within the predicted range. The temperature was higher than expected, but not impossibly so. The magnetic field was detectable, the pressure was low, but every single measurement revealed discrepancies from the theoretical predictions. Small differences, subtle shifts, variations that wouldn't make headlines but force scientists to revise their models. And that's how science actually works. The predictions weren't fundamentally incorrect. They were based on sound physics, careful observations, and decades of research. But they were predictions, educated guesses built on incomplete data. Remote observations can only tell you so much. You can infer density from how starlight scatters. You can estimate temperature from spectral lines. You can model magnetic fields based on theory. But until you put an instrument directly into the medium and measure it, you don't know for certain. Voyager provided those direct measurements, and every one of them required adjustments to the models. Not because the models were bad science, but because reality is always more complex than theory predicts. The interstellar medium isn't uniform. It's clumpy, dynamic, variable. The temperature is higher near the heliopause because the plasma gets compressed there. The density increases with distance from the boundary because of unknown processes that theoretical models hadn't accounted for. Small differences matter. A 10 or 20% variation in density might not sound significant, but when you're trying to understand how the heliosphere interacts with the interstellar medium, or how cosmic rays propagate through space, or what happens when a star moves through different regions of the galaxy, those small variations become critical. They change the shape of the heliosphere. They affect how much radiation reaches Earth. They influence where the heliopause forms and how it behaves. They matter for understanding not just our solar system, but every star system in the galaxy, moving through its own local interstellar environment. Voyager's measurements revealed that the universe doesn't conform neatly to our predictions. It surprises us. It challenges us to refine our understanding, adjust our models, ask better questions. That's what discovery looks like when you're exploring a region no human instrument has ever sampled before. But the measurements themselves weren't the only surprise, because even after Voyager crossed into interstellar space, the Sun's influence didn't end. In fact, scientists discovered that storms on the Sun, eruptions that happened years earlier and millions of miles behind the spacecraft, were still reaching Voyager, launching shockwaves through the interstellar medium itself. Waves that revealed something no one had predicted. The Sun's reach extends far beyond the heliopause, not as solar wind, but as something else entirely. Discovery number 5. The Sun is still reaching Voyager, not as light, not as solar wind, as shock waves, pressure waves launched through the interstellar medium itself by solar storms that erupted years earlier and millions of miles behind the spacecraft. Waves that no one predicted, waves that shouldn't exist. October 23, 2012. 2 months after Voyager 1 crossed the heliopause, the spacecraft's plasma wave instrument detected something faint, a tone, sustained, around 2.1 kilohertz. The plasma around Voyager was vibrating. Electrons were oscillating at a specific frequency, ringing like a struck bell. Don Gurnett, principal investigator for the plasma wave instrument at the University of Iowa, analyzed the signal. The frequency was too high, far too high for the heliosheath. It corresponded to an electron density of about 0.06 particles per cubic centimeter, 40 times denser than the outer heliosphere. This was the signature of interstellar space. But where did the vibration come from? The oscillations lasted from October 23rd through November 27th, 5 weeks, then faded, and for months, silence returned. April 9th, 2013. The plasma wave instrument detected another tone, stronger this time, louder, higher frequency, 2.6 kilohertz. The plasma was vibrating again, excited into motion by something that had passed through. Scientists traced the oscillation backwards. They calculated how long it would take for a pressure wave to travel from the Sun to Voyager 1's position, 11 billion miles away. They looked for solar events that matched the timing. March 2012, 13 months earlier. A coronal mass ejection, a massive burst of hot plasma, had erupted from the Sun. It travelled outward at hundreds of kilometers per second, slamming into the heliopause. The impact launched a shock wave through the interstellar medium, that wave moving far slower than the solar wind but still racing through the near vacuum of space, took 13 months to reach Voyager. When it arrived, it compressed the plasma around the spacecraft, exciting electrons into oscillations that rang out at frequencies Voyager could detect. The Sun 93 million miles from Earth and 11 billion miles from Voyager, had sent a ripple through interstellar space, and Voyager heard it. No model predicted this. Scientists knew that coronal mass ejections, violent eruptions on the Sun that hurl billions of tons of plasma into space, could generate shock waves in the solar wind. These shock waves cause geomagnetic storms on Earth. They disrupt satellites. They accelerate particles to near-light speed. But once the solar wind reached the heliopause, it should stop. The boundary should absorb the impact. Solar influence should end there. Instead, when a coronal mass ejection slams into the heliopause from behind, the impact generates a new shockwave in the interstellar medium itself, not solar wind, not particles from the Sun. A pressure wave traveling through the plasma between stars. Imagine this. Dropping a stone into a still pond creates ripples that spread outward across the surface. The heliopause is not a wall. It's a boundary between two fluids under pressure, hot solar plasma on one side, colder interstellar plasma on the other. When a massive pressure wave from a solar storm hits that boundary, it doesn't just stop, it transfers energy. It launches a new wave into the medium beyond. These waves travel through the interstellar plasma at a fraction of the solar wind's speed, but they travel far, potentially hundreds of astronomical units beyond the heliopause, farther than anyone expected the Sun's influence to reach. And Voyager, drifting through interstellar space, became the first instrument to detect them directly. February 2014, the plasma wave instrument detected oscillations again, the third event, triggered by another solar storm. This one was different. The oscillations didn't fade after weeks. They continued, month after month. The plasma around Voyager remained disturbed, vibrating at frequencies that slowly shifted as the spacecraft moved deeper into interstellar space. By November, 9 months later, the wave was still propagating. Voyager had traveled 250 million miles, 400 million kilometers, during that time, and the shock wave was still detectable. Ed Stone, Voyager's project scientist, described the phenomenon. The tsunami causes the ionized gas that is out there to resonate, to sing or vibrate like a bell ringing in near silence, in a medium so tenuous it would count as a perfect vacuum on Earth, yet dense enough, structured enough to carry waves launched by a star 11 billion miles away. 2015, a fourth detection, another solar storm, another wave. Scientists began to realize that these events were not rare. They were ongoing. The Sun continuously sends shock waves into interstellar space, some stronger, some weaker, some detectable by Voyager, some too faint or too distant. The interstellar medium, which astronomers once assumed was calm and quiet, is turbulent with waves, some launched by the Sun, some by distant supernovae, some by other stars moving through the galaxy. The space between stars is not empty stillness, it's an ocean disturbed by distant storms. Each plasma oscillation allowed scientists to calculate the electron density at Voyager's location, and the measurements revealed something unexpected. The density was increasing. October to November 2012, 0.06 electrons per cubic centimeter. April to May 2013, 0.08. By 2014 and 2015, the density had climbed higher. Voyager was moving away from the heliopause, deeper into interstellar space. The density should have leveled off or decreased. Instead, it rose. Why? Scientists don't know for certain. One theory suggests that the interstellar magnetic field near the heliopause draws particles away, creating a lower density region just beyond the boundary. As Voyager travels farther, it enters denser plasma. Another theory proposes that particles in the interstellar wind slow down when they approach the heliosphere, like traffic slowing near an obstruction, causing a density gradient that increases with distance from the boundary. The plasma oscillations also confirmed beyond doubt that Voyager had crossed the heliopause. The electron density measured during these events was 40 to 80 times higher than anything detected in the heliosheath. That density matched theoretical predictions for the very local interstellar medium. Voyager was truly in interstellar space, and the sun was still shouting across the void. The discovery fundamentally changed how scientists understand the sun's influence. For decades, the heliopause was treated as the edge, the place where the sun's domain ended. Beyond it, interstellar space, governed by galactic forces, untouched by solar activity. But the shock waves revealed that the sun's reach extends far beyond the heliopause, not as a magnetic field, not as solar wind, as pressure, as waves propagating through plasma, carrying energy from solar eruptions into the space between stars. Don Gannett estimated that these waves could travel another 100 astronomical units or more beyond Voyager's position, possibly farther. No one knows where they finally dissipate. No one knows how far the sun's influence truly extends. This has implications. The heliosphere doesn't just shield us from cosmic rays. It actively disturbs the interstellar medium around it. The sun, through its eruptions, its magnetic field, its motion through the galaxy, creates turbulence in the plasma for hundreds of astronomical units in every direction. Every star does this. Every star moving through the interstellar medium generates a bubble, launches waves, disturbs the space around it. The galaxy is not a collection of isolated stellar systems separated by calm voids. It's a dynamic, interconnected medium where stars continuously influence the space between them, and Voyager, 11 billion miles from home, proved it. But the shock waves revealed something else, something stranger. Because as Voyager moved through these oscillations, measuring density and temperature and pressure, the spacecraft's magnetometer was recording the magnetic field's strength and direction. And what it found challenged another fundamental prediction about the boundary between solar and interstellar space, a prediction about how magnetic fields should behave when two vastly different regions meet. Discoveries number 6. Beyond the heliopause, scientists expected clarity. Two distinct regions, two different environments, the sun's magnetic field pointing one way, the galaxy's field pointing another, a clean separation. What Voyager found instead was confusion. August 25, 2012, Voyager 1 crossed the heliopause. Solar particles vanished, cosmic rays surged, the plasma density jumped 80-fold. Every measurement confirmed the spacecraft had entered a fundamentally different region of space, except one. The magnetic field didn't change direction. For decades, every model, every theoretical paper, every prediction about the heliopause said the same thing. When a spacecraft crosses from the solar magnetic field into the interstellar magnetic field, the direction should rotate. Dramatically. The sun's field spirals outward, twisted by the solar wind's rotation. The galaxy's field threads through interstellar space in a different direction entirely. The two fields should be misaligned. Crossing from one to the other should be obvious. Voyager 1's magnetometer detected no rotation. The field direction on the interstellar side looked almost identical to the field direction on the solar side. Same orientation, same angle. Scientists were baffled. Some questioned whether Voyager had truly crossed the heliopause at all. Maybe the spacecraft was trapped in some intermediate region, a boundary layer where solar and interstellar fields mixed. Maybe the heliopause was farther out. Maybe the plasma density measurements were wrong. For over a year, the debate continued. Then Voyager 2 crossed. November 5, 2018. 119 astronomical units from the Sun, and its magnetometer told the same story. The magnetic field changed smoothly across the heliopause. A small shift, a few degrees at most, not the 90-degree rotation many models had predicted. Not the dramatic reorientation that should mark the boundary between two fundamentally different magnetic environments, two spacecraft, separated by over 100 astronomical units, more than 9 billion miles, both crossing at different locations, both during different phases of the solar cycle, both detecting almost no magnetic field rotation. How do you explain that? The first explanation was pure chance. Scientists calculated the direction of the interstellar magnetic field using data from the Interstellar Boundary Explorer, IBEX, a spacecraft that had mapped the structure of the energetic neutral atoms at the edge of the heliosphere. The center of the IBEX ribbon, a circular band of enhanced emissions in the sky, pointed toward the direction of the pristine interstellar magnetic field, and Voyager 1, traveling north of the ecliptic plane, happened to cross the heliopause at precisely the location where the Sun's magnetic field aligned with the galaxy's field. Same direction, same orientation, no rotation to detect. If Voyager had crossed a few years earlier or later, or at a slightly different location, the fields would have been misaligned. The magnetometer would have registered a rotation, but the spacecraft happened to pass through the one region where both fields pointed the same way. Astronomical coincidence, except Voyager 2 found the same thing, and Voyager 2 crossed in the southern hemisphere. 65 degrees away from Voyager 1's trajectory, different location, different part of the heliosphere, different field configuration, yet still almost no rotation. Scientists began to suspect the explanation wasn't coincidence, it was structure. The interstellar magnetic field doesn't hit the heliopause and stop. It drapes around it, bending, twisting, wrapping itself along the boundary like fabric draped over a curved surface. As the field approaches the heliopause, it encounters resistance. The solar wind pushes outward. The interstellar medium pushes inward. The pressure compresses the interstellar field, forcing it to bend. The field lines that were straight and uniform in the undisturbed interstellar medium twist as they approach the heliosphere, acquiring components parallel to the boundary. This draping means the magnetic field direction near the heliopause is not the same as the field direction far out in pristine interstellar space. The boundary itself distorts the field, and depending on where a spacecraft crosses, north, south, east, west, the degree of distortion varies. Voyager 1 crossed at a location where the draped interstellar field happened to align with the solar field. Voyager 2 crossed at a location where the draped field was only slightly misaligned. But here's the problem. 2 data points can't map a 3-dimensional structure. Scientists know the interstellar field is draped. They know it varies with location, but they don't know its full shape. They can't predict how much the field will rotate at any given crossing point without direct measurements. And Voyager is the only spacecraft that has made those measurements. This matters for cosmic rays, because cosmic rays, high-energy particles from distant supernovae and other violent events in the galaxy, don't travel in straight lines. They follow magnetic field lines, they spiral along them, and the structure of the magnetic field near the heliopause determines how easily cosmic rays can enter the heliosphere, which leads to the 7th discovery. Beyond the heliopause, cosmic ray intensity increased. This was expected. The heliosphere shields the inner solar system from galactic cosmic rays. The solar wind and the sun's magnetic field deflect them, scatter them, slow them down, cross the heliopause, and the intensity should jump. Voyager measured that jump, about 20% higher beyond the boundary than just inside. In some energy ranges, the increase was even more dramatic, 2 or 3 times higher. But the intensity increase wasn't the surprise the directional distribution was. Scientists expected cosmic rays in interstellar space to come from all directions roughly equally, isotropic, uniform. The galaxy generates cosmic rays from supernovae scattered throughout the Milky Way. No particular direction should dominate. Voyager detected something else. Shortly after crossing the heliopause, Voyager 1's instruments began recording periodic depletions in cosmic ray intensity. Not overall decreases, the intensity remained elevated compared to the heliosheath, but temporary reductions lasting weeks to months, small, only a few percent, but measurable, repeatable. The low-energy charge particle experiment revealed the pattern. Cosmic rays arriving at 90-degree pitch angles, perpendicular to the magnetic field, were depleted. Particles arriving parallel or anti-parallel to the field remained unchanged. More cosmic rays from some directions, fewer from others. This should not happen in undisturbed interstellar space. Galactic cosmic rays originate from sources scattered across the galaxy. Their distribution should be roughly isotropic once you're outside the heliosphere's influence. But Voyager wasn't detecting isotropy. It was detecting anisotropy, structure, a pitch angle dependent distribution that changed over time in response to pressure waves and disturbances passing through the interstellar medium. The most counterintuitive finding: fewer cosmic rays came from the direction of the galactic center. The galactic center, home to Sagittarius A star, the supermassive black hole at the heart of the Milky Way, surrounded by dense star-forming regions and the highest concentration of supernovae in the galaxy, should be the brightest source of cosmic rays. More stars, more supernovae, more particle acceleration, more cosmic rays streaming outward. Voyager detected fewer from that direction, not dramatically fewer, not zero, just less than expected based on simple models that assumed cosmic rays propagate freely through the galaxy. The explanation lies in magnetic trapping. Cosmic rays don't travel in straight lines. They spiral along magnetic field lines, and the structure of the local interstellar magnetic field, its strength, its direction, its variations, determines which cosmic rays can reach a particular location and which get deflected elsewhere. Near the heliopause, the magnetic field is compressed, distorted, enhanced by the pressure from the solar wind pushing outward. This creates regions where particles with certain pitch angles get trapped, confined to magnetic field lines that curve back on themselves or that guide particles away from Voyager's location. Picture this. Imagine cosmic rays as water flowing through a landscape of invisible channels. The magnetic field creates the channels. Some channels are wide open, allowing particles to flow freely. Others are narrow, twisted, or blocked. The distribution of cosmic rays you detect depends not just on where the particles originate, but on which channels lead to your location. Voyager is detecting cosmic rays filtered by the local magnetic field structure, not the raw distribution from galactic sources, a modified, shaped anisotropic distribution that reveals the invisible magnetic landscape of the very local interstellar medium. Voyager 1 detected anisotropy. Voyager 2, when it crossed in 2018, detected similar patterns. Both spacecraft observed cosmic ray distributions that varied with direction. Both found evidence for magnetic field effects shaping which particles reach their detectors. But two spacecraft, traveling in roughly the same general direction away from the Sun, both heading toward the nose of the heliosphere, can't map the full three-dimensional structure of the interstellar magnetic field. They can't tell you how the anisotropy varies in other directions. They can't reveal the global picture. Scientists know the magnetic field near the heliopause is complex. They know it's not uniform. They know it matters for cosmic ray propagation, but they don't know its full shape, its strength in every direction, its variations over time. Every model of the heliosphere, every prediction about cosmic ray access, every estimate of radiation exposure for future interstellar missions, all of them depend on assumptions about the magnetic field structure that can't be fully tested with just 2 data points. This is the limitation of exploration with single spacecraft. You can discover, you can measure, you can reveal that the universe doesn't conform to your expectations, but you can't map, you can't see the full picture. Voyager found magnetic chaos where scientists expected order. It found cosmic ray anisotropy where models predicted isotropy. It revealed that the boundary between the solar system and interstellar space is not a clean line, but a dynamic, structured, variable interface shaped by forces we're only beginning to understand, and every answer raises new questions, but these discoveries, the prolonged crossing, the boundary that breathes, the magnetic field that refused to rotate, the cosmic rays flowing in unexpected patterns, these weren't Voyager's first surprises. Before the spacecraft ever reached the heliopause, before they crossed into interstellar space, they had already revolutionized our understanding of the outer solar system itself. Because the journey to the edge began 48 years ago, with 2 planets no spacecraft had ever visited, and what Voyager found there rewrote the textbooks. The discoveries at the heliopause, the breathing boundary, the magnetic field that refused to rotate, the cosmic rays flowing in unexpected patterns, these weren't Voyager's first surprises. They were the culmination. Long before either spacecraft reached the edge of the solar system, they had already revolutionized our understanding of the worlds beyond Mars. Every planet they visited revealed something impossible. Every moon defied expectations. Every prediction turned out to be incomplete. What enabled 2 spacecraft, designed for a 5-year mission to Jupiter and Saturn, to reach the boundary between solar and interstellar space 48 years later? The answer begins not at the edge, but at Jupiter. Voyager 1 approached Jupiter on March 5, 1979. Engineers at NASA's Jet Propulsion Laboratory in Pasadena watched as the spacecraft's cameras began returning images from 174,000 miles above the planet's cloud tops. They expected storms. They expected swirling atmospheric features. They had seen Pioneer 10 and Pioneer 11 fly past Jupiter years earlier, capturing blurry images of the giant planet's turbulent atmosphere. But when Voyager's high-resolution cameras revealed the fine structure of Jupiter's atmosphere, the intricate bands of color, the smaller storms rotating around the Great Red Spot, the lightning flashes deep in the clouds, scientists realized how little they actually knew. At the time, the Great Red Spot itself, a storm 3 times the size of Earth, showed internal structure no ground-based telescope had ever resolved. Smaller eddies rotated around it. Wind speeds reached 400 miles per hour. The storm had been raging for at least 300 years, and Voyager's measurements suggested it might persist indefinitely. But Jupiter's atmosphere wasn't the revelation. The revelation was Io. Linda Morabito, a navigation engineer at JPL, was processing images for spacecraft navigation 3 days after Voyager's closest approach. She enhanced an image taken looking back at Io, backlit by the sun, and she saw a plume, a cloud of material rising more than 150 miles above Io's surface. Bright, curved, unmistakable, active volcanism on another world. The first time in human history that volcanic eruptions had been observed beyond Earth. Io, a moon slightly larger than Earth's moon, was supposed to be geologically dead, cold, ancient, cratered. Instead, Voyager found 9 active volcanoes erupting simultaneously. The surface was young, resurfaced so rapidly by volcanic activity that almost no impact craters existed. Sulfur and sulfur dioxide covered the landscape in shades of yellow, orange, red, and black. The heat came from tidal forces. Jupiter's immense gravity, combined with the gravitational tugs from Europa and Ganymede, stretches and compresses Io every 42 hours as the moon's elliptical orbit brings it closer to and farther from the planet. The constant flexing generates friction, heat, melting, volcanism. A new concept entered planetary science: tidal heating. The idea that gravitational forces alone could power geological activity changed how scientists understood moons throughout the solar system. Voyager also discovered Europa's surface of cracked ice, smooth, young, almost crater-free, suggesting a subsurface ocean beneath the frozen crust. That discovery would drive planetary exploration for the next 4 decades, leading to missions like Europa Clipper, designed specifically to investigate whether life could exist in Europa's hidden ocean. Jupiter had faint rings. Voyager found them. 2 new moons, Thebe and Metis, orbiting close to the planet. Lightning, aurora, a magnetosphere far more complex than any model predicted. 4 months later, Voyager 2 confirmed the discoveries. 8 of the 9 volcanoes on Io were still erupting. November 12, 1980, Voyager 1 reached Saturn, passing within 78,000 miles of the planet's cloud tops. Saturn's rings, visible from Earth through even small telescopes, were thought to be relatively simple structures, broad bands of ice and rock particles orbiting the planet. A few gaps, maybe some waves or ripples caused by gravitational interactions with nearby moons. Voyager revealed thousands of individual ringlets, intricate structure, braided rings, gaps cleared by shepherd moons, small satellites like Prometheus and Pandora that gravitationally confine ring particles, keeping certain rings narrow and well-defined. The F ring, discovered by Pioneer 11, turned out to be kinked, braided, and constantly changing. Prometheus and Pandora orbited on either side of it, their gravitational influence sculpting its shape. Saturn's atmosphere showed storms, wind patterns, and features that changed over the months between Voyager 1 and Voyager 2's encounters. The planet was more dynamic than expected, but the most important target at Saturn wasn't the planet itself, it was Titan. Voyager 1 had to choose between 2 trajectories. One would send it toward Pluto, the other would take it close to Titan. Scientists chose Titan because Titan had an atmosphere, not a thin wisp of gas, a thick atmosphere. Voyager's instruments measured surface pressure at 1.5 bars, 50% higher than Earth's sea level pressure. The atmosphere was mostly nitrogen, like Earth's, but with methane mixed in. Dense photochemical haze, organic compounds created by sunlight breaking apart methane, shrouded the entire moon in an orange fog so thick that Voyager's cameras couldn't see the surface. No one had ever observed a moon with an atmosphere denser than Earth's. Titan became a priority target for future missions. Cassini-Huygens, launched in 1997, would spend 13 years exploring the Saturnian system, with dozens of flybys of Titan revealing lakes of liquid methane on the surface, rivers, rainfall, weather, a hydrological cycle using hydrocarbons instead of water, all because Voyager revealed that Titan was fundamentally different from every other moon. August 26, 1981. Voyager 2 flew past Saturn at 101,000 kilometers above the cloud tops. Its trajectory allowed closer approaches to several moons Voyager 1 had missed. The spacecraft confirmed the discoveries, added new details about the rings, and then used Saturn's gravity to redirect itself toward Uranus. The original 5-year mission, Jupiter and Saturn, was complete, but Voyager 2 was still operational. Its instruments still worked. Its radioisotope thermoelectric generators still produced power. Engineers calculated trajectories. Scientists debated priorities. January 8, 1981. NASA approved the extended mission. Voyager 2 would continue to Uranus. January 24, 1986. Voyager 2 passed within 50,600 miles of Uranus's cloud tops. No spacecraft had ever visited Uranus. Ground-based telescopes showed a featureless blue-green disk. Speculation suggested a cold, quiet world with little atmospheric activity. Voyager found a planet tipped on its side, axial tilt, 97.8 degrees. Uranus orbits the Sun rolling like a barrel, with one pole pointing almost directly at the Sun during solstice, then the other pole 21 years later. This creates the most extreme seasonal variations in the solar system. The planet's magnetic field was tilted 59 degrees from its rotational axis and offset from the center by 1/3 of the planet's radius. Unlike any planetary magnetic field observed before, a helix-shaped magnetic tail stretched millions of miles away from the Sun. Wind speeds reach 560 miles per hour, despite receiving only 1/400th the sunlight Earth receives. Voyager discovered 10 new moons, 2 new rings, and revealed that Uranus's 5 large moons each had unique geological histories. Miranda, the innermost large moon, shocked scientists. Its surface was a patchwork of terrains that didn't belong together. Huge canyons, some up to 12 miles deep, terraced layers, old, heavily cratered regions next to young, smooth regions with parallel ridges and grooves forming chevron patterns. The moon looked shattered and reassembled. One hypothesis suggested Miranda had been broken apart by a violent impact and then gravitationally reaggregated, the pieces coming back together, but not in their original configuration. Another theory proposed that tidal heating and internal geological activity had resurfaced parts of the moon at different times, creating the patchwork appearance. No one had seen anything like it. Uranus itself, its bizarre magnetic field, its sideways rotation, its active atmosphere despite extreme cold, every measurement contradicted the assumption that the outer solar system was quiet and simple. August 25, 1989, 12 years after launch. Voyager 2 made its closest approach to Neptune at 4,950 kilometers above the planet's north pole. Neptune, 30 times farther from the Sun than Earth, receives 1/1000th the sunlight Earth does. Scientists expected a cold, dark, placid world, minimal atmospheric activity, maybe some faint cloud features. Instead, Voyager found the most violent atmosphere in the solar system. The Great Dark Spot, a storm the size of Earth, raged in Neptune's southern hemisphere. Winds around the storm reached 1,300 miles per hour, 2,100 kilometers per hour, faster than any winds measured on any other planet, faster than Saturn, faster than Jupiter, faster than anything predicted. Small, bright clouds, nicknamed Scooter, raced around the planet at 400 miles per hour. The atmosphere churned with storms, bands, and rapidly changing features despite the planet's enormous distance from the Sun and correspondingly low energy input. The heat driving Neptune's atmospheric dynamics came mostly from inside the planet itself. Internal heat left over from formation, slowly radiating outward, creating convection and weather patterns in the thin, frigid atmosphere. Voyager also discovered 6 new moons and 4 faint rings. But the most remarkable discovery came 5 hours after passing Neptune, when Voyager flew within 25,000 miles of Triton, Neptune's largest moon. Triton's surface temperature, -391 degrees Fahrenheit, -235 degrees Celsius, the coldest surface temperature measured by Voyager anywhere in the solar system. At that temperature, nitrogen freezes solid. Methane ice covers parts of the surface in a pinkish polar cap. The moon should be geologically dead, frozen, inert. Voyager's cameras captured geysers, dark plumes rising up to 5 miles above Triton's surface. Nitrogen geysers, gas erupting from beneath the surface, driven not by internal heat, but by sunlight warming the nitrogen ice during Triton's brief polar summer. The gas bursts through weak spots in the crust, carrying dark dust that deposits back onto the surface in long streaks visible in Voyager's images. Triton's surface showed relatively few impact craters. Large areas had been resurfaced geologically recently. Cracks, ridges, smooth plains of frozen material that had flowed and solidified. The moon orbits Neptune backwards, retrograde orbit, opposite the planet's rotation. This strongly suggests Triton didn't form with Neptune. It was captured, probably a Kuiper Belt object that wandered too close and was gravitationally trapped billions of years ago. That capture would have been violent. Tidal forces would have heated Triton's interior, possibly melting it entirely before it settled into its current stable orbit and froze. Even now, Triton is slowly spiraling inward toward Neptune. In tens of millions of years, a short time cosmically, tidal forces will rip the moon apart, potentially creating a ring system around Neptune more spectacular than Saturn's. Voyager 2's encounter with Triton was the last planetary flyby. The spacecraft had visited 4 giant planets, explored dozens of moons, discovered rings, volcanoes, geysers, atmospheres, magnetic fields, and dynamic processes no one had anticipated. Every world had been a surprise, every prediction incomplete, every model revised. September 12, 1989. Following the Neptune encounter, NASA officially designated the extended mission as the Voyager interstellar mission. Both spacecraft were still operational. Both were traveling fast enough to escape the solar system. Both carried functioning instruments that could measure the solar wind, magnetic fields, cosmic rays, and plasma as they journeyed outward. Scientists realized Voyager could answer a question no one had been able to address before. Where does the sun's influence end? The mission had been designed to last 5 years, 1977 to 1982. Jupiter and Saturn, then silence. Instead, the spacecraft kept working. Engineers at JPL continued sending commands. Scientists continued analyzing data. The Deep Space Network continued tracking the faint radio signals. Years became decades. Instruments were shut down one by one to conserve power. The cameras, no longer needed in the darkness beyond the planets, were turned off after the Neptune encounter. Other instruments followed as power from the radioisotope thermoelectric generators declined. But the plasma instruments, magnetometers, cosmic ray detectors, and plasma wave instruments remained active, enough to measure the environment, enough to detect the heliopause when the spacecraft finally reached it. Voyager 1, August 25th, 2012, 121 astronomical units from the Sun. Voyager 2, November 5th, 2018, 119 astronomical units. Both spacecraft crossed into interstellar space. Both detected the prolonged, complex, dynamic transition no model had predicted. Both found that every detail at the edge, the boundary's location, its thickness, its behavior, the magnetic field, the cosmic rays, was different from expectations, just like Jupiter, just like Saturn, just like Uranus, just like Neptune. The pattern held. The universe, at every scale, refuses to conform to our predictions. Voyager proved this at the planets, then proved it again at the heliopause. And the spacecraft are still out there, still traveling, still sending data. 48 years after launch, 10 times longer than their design lifetime. The most profound discoveries didn't happen at Jupiter or Saturn or Neptune. They happened at the edge, in the place where the solar system ends and interstellar space begins. In the boundary region no human instrument had ever sampled before. A boundary that turned out to be more complex, more dynamic, and more surprising than anyone imagined. But crossing the heliopause was only the beginning of a larger question. Because Voyager's journey to the edge revealed something fundamental about the challenge of leaving the solar system. The distances are vast, the speeds are slow, the environment is hostile in ways we're only beginning to understand. And if humanity ever hopes to send spacecraft, or perhaps one day people, to other stars, we must first confront what Voyager learned about the true scale of interstellar space. Voyager proved we can reach the edge. It measured the boundary. It crossed into interstellar space. It sent back data from a region no human instrument had ever sampled. But reaching the edge is not the same as leaving. The heliopause, 120 astronomical units from the Sun, marks where the solar wind stops, where the Sun's magnetic influence fades, where cosmic rays from distant supernovae become the dominant radiation. But it's not the edge of the solar system, not gravitationally, not structurally, not in any practical sense for a spacecraft trying to reach another star, because beyond the heliopause lies the Oort cloud, a vast spherical shell of icy objects extending perhaps 30,000 astronomical units from the Sun, 1,000 times farther than the heliopause. Voyager will reach its inner edge in about 300 years. It will take 30,000 years to pass through. And beyond the Oort cloud, beyond the last gravitational whisper of our Sun's influence, lies the true void, the space between stars, 4.2 light-years to Proxima Centauri, the closest star to the Sun, 268,000 astronomical units. At Voyager's speed, 38,000 miles per hour, 17 kilometers per second, the journey would take 73,775 years. 73,000 years ago, modern humans were migrating out of Africa. Neanderthals still roamed Europe. The last ice age hadn't peaked. Language was young. Writing didn't exist. Cities didn't exist. Agriculture didn't exist. If Voyager had launched then, travelling at its current speed toward Proxima Centauri, it would be arriving now. The discoveries at the heliopause weren't just scientific curiosities. They were warnings. Voyager revealed what interstellar space actually contains, and every measurement matters for any future spacecraft trying to cross it at high speed. The interstellar medium, 0.08, particles per cubic centimetre, sounds empty. It is empty compared to Earth's atmosphere. But at 10% the speed of light, the minimum speed needed for reasonable interstellar travel times, those sparse particles become a sandblaster. Imagine driving into rain. At 30 miles per hour, raindrops hit your windshield gently. At 60 miles per hour, they hit harder. At 300 miles per hour, they hit like bullets. Now, imagine traveling at 18,000 miles per second, 67 million miles per hour, 10% of light speed. Every hydrogen atom you encounter hits with the kinetic energy of a high-speed projectile. Every grain of dust becomes a micrometeorite capable of punching through metal. Voyager travels slowly enough that this isn't a problem, but a fast interstellar spacecraft would need shielding, armor, magnetic deflectors, something to protect it from the medium itself. Voyager also revealed cosmic ray intensity beyond the heliopause, 20% higher than inside, in some energy ranges 2 to 3 times higher, and the anisotropy, the directional variation, means radiation exposure depends on which direction you're traveling. A crewed interstellar mission would face radiation levels no human has ever experienced for extended periods. Not just solar radiation, galactic cosmic rays, high-energy particles accelerated by supernovae thousands of light-years away, traveling near light speed, capable of penetrating spacecraft hulls and damaging DNA. The dynamic environment Voyager discovered matters too. Shockwaves from the Sun propagate hundreds of astronomical units into interstellar space. The heliopause breathes, expanding and contracting by several astronomical units. The magnetic field near the boundary is complex, structured, variable. An interstellar spacecraft can't just point at a star and go. It has to navigate through a boundary region that moves, through plasma oscillations and pressure waves, through a magnetic field that varies with location and time, through an environment that's far more turbulent and structured than anyone predicted before Voyager measured it directly. And the distance to the heliopause itself, 121 astronomical units, not 90, matters. Every additional astronomical unit adds distance, adds time, adds fuel requirements for any propulsion system trying to accelerate a spacecraft to interstellar speeds. Voyager proved we can build machines that survive, that function for decades in the harsh environment of deep space, that cross into interstellar space and keep transmitting. But Voyager also proved that the distances are more daunting than we imagined, the environment more complex, the challenges more fundamental. February 14th, 1990. 40 astronomical units from the Sun, 3.7 billion miles. Voyager 1 received a command from Earth. Turn around. Look back. One last time. The spacecraft rotated. Its cameras, which had been pointed forward into the darkness for the entire journey beyond Saturn, swiveled. The imaging platform moved slowly. Engineers were cautious about damaging systems that had been idle for years. Voyager aimed its narrow-angle camera at 6 planets scattered across the sky: Venus, Earth, Jupiter, Saturn, Uranus, Neptune, a family portrait of the solar system from the outside. The images were stored on the spacecraft's tape recorder, then transmitted to Earth over the following weeks. 5.5 hours for each signal to cross the void at the speed of light. When the data arrived, scientists assembled the images, and one of them showed Earth, a pale blue dot, less than a single pixel, suspended in a shaft of scattered sunlight, against the black. Carl Sagan, who had advocated for the photograph, who had convinced NASA to take it despite concerns about pointing the camera near the sun, wrote about what he saw. "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. Every war, every discovery, every moment of human history, on a dot so small it almost disappears in the vastness. The photograph was taken from 40 astronomical units, from just beyond the orbit of Neptune, still deep inside the solar system by any gravitational measure, still within the heliosphere, still protected by the bubble of solar wind that shields us from the worst of interstellar radiation. And yet from that distance, Earth was already invisible to the naked eye, a faint speck requiring long exposures and careful image processing to even detect. Voyager is now 170 astronomical units from the Sun, 4 times farther than when it took the pale blue dot image. From Voyager's current position, if the cameras were still working, Earth would be 4 times dimmer, even harder to see. In interstellar space, from beyond the heliopause, Earth is lost in the glare of the Sun, impossible to resolve, invisible. The solar system that feels so large when you're inside it, Mercury to Neptune spanning 30 astronomical units, a gap so vast that light takes 4 hours to cross it, becomes a point, a single star among 400 billion, unremarkable, ordinary, one of countless stellar systems scattered through the galaxy. Voyager's discoveries at the heliopause revealed how little we knew about our own cosmic neighborhood, the heliosphere's shape, its asymmetry, the boundaries' complexity, the breathing motion, the magnetic field structure, the plasma oscillations propagating into interstellar space. We're still inside the solar system's gravitational sphere of influence, still within the region where the sun's gravity is the dominant force, and we're only beginning to understand it. The heliopause is not the edge, it's a boundary between 2 environments, a transition, a place where solar plasma meets interstellar plasma and pressure balances. But the sun's gravity extends far beyond, thousands of astronomical units through the Oort cloud. The closest star, Proxima Centauri, is 268,000 astronomical units away, 600 times farther than the heliopause. If we scaled the solar system so that Earth's orbit around the Sun was the size of a quarter, 1 inch in diameter, the heliopause would be 10 feet away. Proxima Centauri would be a mile away. The galaxy contains 400 billion stars. Most have their own heliospheres, their own heliopauses, their own complex boundary regions where stellar winds collide with the interstellar medium. And the interstellar medium itself varies. Denser in some regions, less dense in others. Threaded with magnetic fields that guide cosmic rays and shape how stellar systems interact with their surroundings. We've crossed the heliopause with 2 spacecraft. We've sampled the very local interstellar medium in 2 locations. We've begun to understand the structure of the boundary, but we're still learning, still discovering, still surprised by measurements that don't match predictions. Voyager taught us humility. It taught us that the universe doesn't conform to our models, that every boundary, every transition, every environment we encounter for the first time reveals complexities we didn't anticipate. The edge of the solar system turned out to be more interesting, more dynamic, more structured than anyone imagined. And if the edge is this complex, what does that say about the space beyond? But Voyager carries more than instruments, more than cameras and magnetometers and cosmic ray detectors. Each spacecraft carries a message, a record of who we are, what we've made, the sounds of our world, greetings in 55 languages, music from 6 continents, a message designed to last billions of years, longer than our civilization, longer perhaps than our species. A message now drifting through interstellar space, carrying the essence of humanity into the cosmic ocean. The deadline was impossible, 6 weeks. That's what NASA gave Carl Sagan's team to create a message that would outlast human civilization. A phonograph record, gold-plated copper, 12 inches in diameter, designed to survive not years or centuries, but billions of years, longer than continents, longer than species, longer than the recognizable shape of the night sky. What do you say to eternity? The team assembled in the summer of 1977. Carl Sagan from Cornell University, Frank Drake, architect of the first systematic search for extraterrestrial intelligence, Anne Droyan, creative director, Timothy Ferris, producer, John Lomberg, designer, Linda Salzman, organizing greetings from around the world. They had months to distill 4.5 billion years of Earth story into 90 minutes of audio and 115 images encoded into grooves on a copper disc. Not a comprehensive archive, a curated introduction, the first impression of humanity sent beyond, the boundary of our sun's influence. Start with the universal language, mathematics, physics, the structure of hydrogen, the most common element in the universe, directions etched on the aluminum cover, a pulsar map showing Earth's location relative to 14 pulsars, cosmic lighthouses whose precise timing signatures could serve as navigational references for billions of years. Then the sounds, wind sweeping across open plains, thunder rolling through storm clouds, surf crashing against coastlines, the eruption of volcanoes, Earth's ancient violence frozen in sound, life, crickets singing in darkness, frogs calling from wetlands, birds at dawn, humpback whales, their haunting songs recorded in 1970 by marine biologist Roger Payne, revealing intelligence we hadn't fully understood. Human sounds, a baby crying, footsteps, laughter, the sound of a kiss, a heartbeat, the rhythm that drives every human life from first breath to last. Tools and machines, a hammer, striking metal, a saw cutting wood, a tractor working fields, transportation evolving, horse cart, train, jet engine, the roar of a Saturn V rocket launching toward the moon. Greetings in 55 languages, starting with Akkadian, spoken in Sumer 6,000 years ago when writing was still young, ending with Wu, a modern Chinese dialect, every continent, ancient and contemporary, a 5-year-old child saying hello, humanity speaking across time, 90 minutes of music, Johann Sebastian Bach's Brandenburg Concerto No. 2 and the Well-Tempered Clavier, Ludwig van Beethoven's Fifth Symphony and the Cavatina from String Quartet No. 13, Wolfgang Amadeus Mozart's The Magic Flute, Igor Stravinsky, but also Chuck Berry's Johnny B. Good, rock and roll, the music of motion of going somewhere you've never been against impossible odds, music from India, China, Japan, Senegal, Zaire, Peru, the Solomon Islands, Mexico, Azerbaijan, music spanning cultures and centuries, the universal human impulse to create patterns in sound that move the heart, 115 images encoded into the grooves, mathematical and physical definitions first, establishing scales of size, time, mass, then Earth from space, continental drift, the structure of DNA, human anatomy, conception, birth, nursing mothers, children, families, agriculture, cities, the Golden Gate Bridge, the Great Wall of China, the Taj Mahal, the Sydney Opera House, human achievements rendered in light and shadow, frozen in analog code, and hidden in the audio, something more intimate, an hour-long recording of brainwaves and heartbeat, androions, compressed into 1 minute of strange crackling sound, the electrical impulses of a human nervous system translated into audio, thinking, feeling, alive. What was she thinking during that recording? 2 days before the electroencephalogram, Anne Dryan and Carl Sagan had declared their love for each other, not gradually, not carefully. A phone call about finding a piece of ancient Chinese music for the record, flowing stream, 2,500 years old, turned into a confession, then a proposal, then the realization that something profound and unexpected had ignited between them during the work. It was this great eureka moment, Druyan later recalled. It was like a scientific discovery. So when she sat in Bellevue Hospital in New York City, electrodes attached to her scalp, and meditated while the machines recorded the firing patterns of neurons and the rhythm of her heartbeat, part of what moved through her mind was the wonder of love, the newness of it, the improbability, the feeling of connection that transcends language and culture and time. That recording is on the golden record. Traveling through interstellar space, a pattern of electrical activity from a human brain newly in love, compressed into sound waves etched in gold. Imagine that. Imagine being the first to decode it, to translate those strange fluctuations back into the patterns of thought and feeling that generated them, to glimpse, even faintly, the inner life of someone from a distant world, someone who lived billions of years ago, someone who was thinking about love while her civilization prepared to send greetings into the cosmic ocean. The chance that anyone will ever hear it is essentially zero. The chance that anyone will ever translate it back into recognizable thought is even smaller. But it's there, a message in a bottle, a record of one moment of human consciousness, preserved in metal that will outlast mountains. The debates were constant. Should they include images of war, disease, poverty, the darker realities of human existence? The team chose not to, not because these things don't exist, not because they wanted to lie, but because the record was an introduction, a greeting, a gesture of friendship extended across unimaginable distance and time to beings we might never meet. You don't begin a conversation with your worst moments. You begin with your best intentions. The Beatles wanted "Here Comes the Sun" included. The band favoured it, but EMI, the company holding the copyright, declined. Too legally complicated, too uncertain. Anne Druyan later reflected on the absurdity. Here's a chance to send a piece of music into the distant future and distant time, and to give it this kind of immortality, and they're worried about money. NASA had received criticism over nudity on the Pioneer plaques. Simple line drawings of a naked man and woman attached to the Pioneer 10 and 11 spacecraft, launched earlier in the decade. For the golden record, the agency chose caution. No photograph of nude adults. Instead, a silhouette. The outline of a man and pregnant woman holding hands, the fetus visible within her womb. Life, connection, the biological reality of how we continue. Every choice was a compromise between what they wanted to say and what was possible to say, between completeness and constraints, between representing Earth as it truly was and representing our hopes for what it could become. The record was not a comprehensive archive. It was a curated moment, a snapshot of humanity at a specific point in time, divided into nation-states but rapidly becoming a global civilization, flawed, striving, reaching outward with messages of peace despite our conflicts. President Jimmy Carter wrote a message included as images on the record. It reads, in part, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts and our feelings. We are attempting to survive our time, so we may live into yours." That sentence carries weight. We are attempting to survive our time, not certain we will, not claiming we have solved the problems that threaten us, just attempting, hoping, extending a greeting into the future with the quiet acknowledgement that our own future is uncertain. Carl Sagan knew the mathematics. Space is vast, the distance between stars immense. The probability that either Voyager spacecraft will ever pass close enough to another planetary system to be detected is vanishingly small. Voyager 1 will pass within 1.6 light-years of the star Gliese, 445 in about 40,000 years. Close in cosmic terms, but still over 9 trillion miles away. Too far for detection by anything except an active search specifically looking for small, silent objects drifting through the void. The spacecraft will be encountered, and the record played only if there are advanced spacefaring civilizations in interstellar space actively searching for artifacts from other worlds. The chances approach zero, so why create the record at all? Because, as Sagan noted, the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The act of creating the record mattered more than the possibility of its discovery. It was an exercise in thinking beyond ourselves, in choosing what to preserve, in wrestling with questions that had no clear answers. What defines humanity? What would we want others to know about us? What do we value? What brings us joy? What connects us across cultures and time? The record forced its creators to look at Earth from the outside, to see our world as a small, fragile place in a vast universe, to recognize that despite our divisions, we are one species on one planet with one shared story. That perspective shift, that moment of stepping back and seeing ourselves as part of something larger, was the real message. Not the content on the record, the consciousness required to create it. The gold plating happened on August 23, 1977. 8 Voyager records cut and plated at the James G. Lee Record Processing Center in Gardena, California. Then mounted in protective aluminum jackets and delivered to the Jet Propulsion Laboratory. Voyager 2 launched August 20th. Voyager 1 launched September 5th. Each carried a golden record attached to its exterior. 12 inches of gold-plated copper encased in aluminum, instructions etched on the cover. A sample of uranium-238 electroplated onto the surface, a radioactive clock with a half-life of 4.468 billion years, allowing any finder to calculate how long the record had been travelling by measuring the decay ratio. An inscription hand-etched into the dead wax. To the makers of music, all worlds, all times. Both spacecraft are now in interstellar space, beyond the heliopause, beyond the region where the solar wind dominates, in the realm where cosmic rays from distant supernovae outnumber particles from the Sun. The golden record is no longer in the solar system's protective bubble. It's in the interstellar medium, the space between stars, the true cosmic ocean. In about 300 years, Voyager will reach the inner edge of the Oort cloud, the vast shell of icy objects orbiting the Sun at distances up to 30,000 astronomical units. It will take 30,000 years to pass through. The spacecraft will drift for millions of years, tens of millions, hundreds of millions, rotating slowly, silent, the instruments long dead, the power supplies exhausted, the transmitters cold, but the record will endure. Gold resists corrosion. Copper provides structural stability. The aluminum jacket shields it from micrometeorite impacts and radiation. The grooves remain. The information persists. In 1 billion years, the continents on Earth will have shifted. Mountain ranges will have risen and eroded. Species will have evolved and gone extinct. Humanity, if it still exists, will be unrecognizable. But the golden record will still carry the sounds of wind and whales and laughter, the music of Bach and Chuck Berry, greetings in 55 languages, images of a world that may no longer exist, a message in a bottle, not sent with the expectation of a reply, sent because the act of sending it changed how we saw ourselves. But the message is not the only legacy. The spacecraft themselves, fragile, aging, constructed with 1970s technology, are still functioning, still transmitting, still sending data across 15 billion miles of space. They were designed to last 5 years. They have lasted 50. And as their power fades and their instruments shut down one by one, they face the final chapter of their mission. Not a dramatic ending, a gradual silence, the slow dimming of humanity's farthest voice. 15.8 billion miles from Earth, 170 astronomical units from the Sun, Voyager 1 continues to transmit. The signal takes 23 hours, 32 minutes, and 35 seconds to reach the Deep Space Network antennas scattered across 3 continents. A 23-watt transmitter, weaker than a refrigerator light bulb, sending data across the void at the speed of light. By the time the signal arrives, spread across billions of miles, its strength has diminished to 1/quintillionth of a watt, barely enough to move a speck of dust, but enough to be detected, amplified, decoded, transformed back into measurements of magnetic fields and cosmic ray intensities and plasma oscillations in the interstellar medium. The spacecraft is dying, slowly, inevitably. Not from damage or catastrophic failure, from entropy, from the inexorable decay of plutonium-238 in the radioisotope thermoelectric generators that have powered it for nearly 50 years. At launch in 1977, the 3 RTGs generated 470 watts of electricity, enough to power the instruments, the computers, the transmitter, the heaters that keep critical systems from freezing, the gyroscopes that orient the high-gain antenna toward Earth. In 2026, Voyager 1 has 239 watts remaining, a 4-watt margin between operational and silent. Every year, the spacecraft loses another 4 watts. Every year, engineers at the Jet Propulsion Laboratory make new calculations. Which instrument can we sacrifice? Which heater can we disable? How much longer can we keep the spacecraft functioning before the power drops below the threshold needed to transmit? In February 2025, NASA shut down the cosmic ray subsystem on Voyager 1, the instrument that helped determine when the spacecraft crossed the heliopause, the instrument that measured the spike in galactic cosmic rays that confirmed Voyager had entered interstellar space, turned off, power diverted to other systems, one less voice in the data stream. Voyager 2's plasma science instrument shut down in October 2024. Its low-energy charged particle instrument, scheduled for shutdown in 2026. One by one, the instruments fall silent. The spacecraft continues, but with fewer eyes, fewer sensors, less capacity to measure the environment it's passing through. Science operations are expected to continue until sometime between 2025 and 2030. Maybe a few years beyond if engineers find more power reserves to tap, more systems to disable, more ways to squeeze functionality from diminishing watts. Engineering signals, the basic telemetry that confirms the spacecraft is alive, oriented, transmitting, could persist until 2036, 2 decades from now, 60 years after launch. Then silence. But silence doesn't mean stopped. Voyager 1 will continue moving at 38,000 miles per hour, 61,000 kilometers per hour, 17 kilometers per second, forever. There's no friction in space to slow it down, no atmosphere, no drag, No force acting against its motion except the faint gravitational pull of distant stars, so weak across such vast distances that it has no measurable effect on the spacecraft's trajectory over human timescales. The spacecraft will drift, cold, dark, silent, the instruments dead, the transmitter cold, the computers offline, the golden record intact, rotating slowly as the spacecraft tumbles through the void. In about 300 years, Voyager will reach the inner edge of the Oort cloud, the vast shell of icy bodies orbiting the Sun at distances up to 30,000 astronomical units. It will take 30,000 years to pass through. 30,000 years of drifting through a region we've never visited, past objects we've never seen, in darkness so complete that the Sun is just another star. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. Not close enough to be captured by its gravity, not close enough to be detected unless someone is specifically searching for small, ancient, silent objects drifting through interstellar space, but closer than it will come to any other star for hundreds of thousands of years. Voyager 2 will pass the star Ross 248 in about 42,000 years at a distance of 1.7 light-years. Both spacecraft will orbit the Milky Way galaxy along with the Sun and all the other stars in our local neighborhood. One complete orbit every 225 million years. The spacecraft were launched when dinosaurs had been extinct for 65 million years. By the time they complete a single orbit of the galaxy, continents will have moved. Species will have evolved and gone extinct. The Earth's surface will be unrecognizable. But the golden record will still carry the sounds of wind and whales and laughter, the music of Bach and Chuck Berry, greetings in 55 languages, images of a world that existed for a brief moment in cosmic time. The records are designed to last billions of years. Gold-plated copper, protected by aluminum jackets, the grooves carrying analog information, sound waves and images encoded as physical patterns, resistant to radiation, to micrometeorite impacts, to the slow passage of eons. Long after humanity is gone, transformed beyond recognition or extinct, the records will persist. Humanity's first interstellar ambassadors. Our message in a cosmic bottle, $865 million. The total cost of the Voyager mission from May 1972 through the Neptune encounter in August 1989, including launch vehicles, spacecraft construction, radioisotope power sources, deep space network tracking support, mission operations, adjusted for inflation, roughly 8 cents per person in the United States per year, half the cost of a candy bar annually since project inception. The return was incalculable. Every textbook about the outer solar system uses Voyager data. Every understanding of Jupiter's atmosphere, Saturn's rings, Uranus's tilted magnetic field, Neptune's winds, every model of tidal heating that explains Io's volcanoes and suggests subsurface oceans on Europa and Enceladus, every measurement of planetary magnetic fields and radiation belts and ring dynamics. Voyager revolutionized planetary science. It revealed that moons could be geologically active, that rings could be structured by shepherd moons and orbital resonances, that ice could flow like rock given enough time and pressure, that the outer solar system was far more complex, more dynamic, more interesting than anyone had predicted. The only spacecraft to visit Uranus and Neptune, the only direct observations we have of those worlds, the only measurements of their magnetic fields, their atmospheres, their moons, their rings, then the edge, 7 discoveries that defied every prediction. The heliopause was 21 astronomical units farther than expected, not 90 to 100 astronomical units, but 121 astronomical units for Voyager 1, 119 astronomical units for Voyager 2, 2.4 billion miles beyond where scientists predicted the boundary would be, the heliosphere's shape, not a sphere, but a bullet, compressed at the front by the sun's motion through the galaxy, flattened at the sides, stretched into a tail that extends hundreds of astronomical units. The crossing itself, not clean, not quick, but complex. Voyager 1's approach took 2 years. The magnetic highway, a structure no one predicted, where solar and galactic magnetic field lines aligned and particles flowed both directions. The boundary breathing, expanding and contracting by several astronomical units over weeks and months. Interstellar space revealed for the first time through direct measurement, not theoretical models, actual data. Density, 0.08 particles per cubic centimetre. Temperature, 54,000 to 90,000 degrees Fahrenheit, but so diffuse you'd freeze. Magnetic field strength, 50 nanotesla, 1/1,000,000th of Earth's. Plasma oscillations propagating through the medium like ripples in a pond. The sun's influence extending far beyond the heliopause through shockwaves launched by solar storms. Tsunamis in interstellar plasma detectable years after the events that created them. Magnetic field orientation. Voyager 1 detected no rotation at the crossing because the galactic field happened to align with the sun's, pure coincidence. Voyager 2 detected only 20 degrees of rotation. The field structure more complex, more variable than models predicted. Cosmic ray intensity and anisotropy. The radiation stronger beyond the heliopause as expected, but the directional distribution surprising. More from some directions, less from others. Less from the galactic center. Counterintuitive, since that's where most sources should be. The magnetic field trapping and guiding particles in ways no simple model captured. 7 ways the observations contradicted predictions. Not fundamentally wrong. The heliosphere exists. The termination shock exists. The heliopause exists. The basic physics was correct, but every detail incorrect. Science is messy. We predict based on the best available theory and limited data. We build models. We make assumptions. Then we measure. And the universe surprises us. And we revise. And we learn. Voyager taught us that even at the edge of our own cosmic neighborhood, we don't fully understand what's happening. That boundaries are more complex than we imagined. That every environment we encounter for the first time reveals structure and dynamics we failed to anticipate. If the edge is this complicated, what does that tell us about the rest of the universe? There's a concept in development, a proposed mission, not yet approved, not yet funded, but studied in detail by a team of over 500 scientists and engineers led by Johns Hopkins University Applied Physics Laboratory, the Interstellar Probe, a spacecraft designed to reach 500 to 1,000 astronomical units in 50 years, 2 to 4 times faster than Voyager, using a Jupiter gravity assist and solar Oberth maneuver, diving close to the Sun to gain velocity from its gravitational field, to achieve speeds of 6 to 7 astronomical units per year. Launch window, earliest in the 2030s, maybe 2036, maybe 2041. Results? 2080 something. The scientists designing the mission won't see the data. Most of them will be retired or dead by the time the spacecraft reaches its primary science targets, deep in the interstellar medium. They're planning a mission whose results will be analysed by the next generation, or the one after that. This is what deep space exploration has become. Science spanning generations, questions posed by one cohort of researchers, answered decades later by their successors. Knowledge built slowly, incrementally across the arc of human lifetimes. The Interstellar Probe would carry modern instruments, better sensitivity, higher resolution, more comprehensive measurements of the heliosphere's structure, the interstellar magnetic field, the distribution of cosmic rays, the properties of interstellar dust and gas. It would travel faster and farther, revealing how the heliosphere changes with distance, how the sun's influence finally fades completely, what the local interstellar medium looks like hundreds of astronomical units from home. It would be Voyager's successor. Not a replacement. Nothing could replace what Voyager accomplished, but a continuation. The next chapter in humanity's exploration beyond the solar system. If it's approved, if it's funded, if it launches in the 2030s as planned. Science doesn't move quickly. It moves deliberately, carefully, with long gaps between missions because resources are limited and priorities shift and political will fades and returns. But the knowledge is permanent. The data Voyager sent back doesn't fade. The measurements don't degrade. The discoveries remain. The spacecraft will die. The knowledge lives. We have traveled a long way together. From the grand tour concept in the 1960s, through the planetary encounters of the 70s and 80s, through the slow journey to the edge, through 7 discoveries that defied every prediction, to this moment, 50 years after launch, as the power fades and the instruments shut down one by one. Voyager was built to last 5 years. It has lasted 50. It crossed boundaries no one expected it to reach. It measured phenomena no one predicted it would encounter. It revealed a solar system more complex and more beautiful than anyone imagined. And in doing so, it changed how we see our place in the universe. The scientists were wrong about the edge. Not in the fundamentals. They understood the basic physics of how solar wind creates a protective bubble around the solar system, but in the details, in the distance, in the shape, in the complexity of the boundary, in the structure of interstellar space beyond. Every prediction missed something. Every model simplified something that turned out to matter. And that's not a failure. That's how science works. You can't know what you'll find until you go there and measure it. You can't predict the details of an environment no instrument has ever sampled. You build the best model you can with the data available. You make predictions, you send a spacecraft, and then you discover how the universe actually behaves. Voyager proved that even our own cosmic backyard holds surprises, that the boundary between solar and interstellar space is not a simple line but a dynamic, structured breathing region that changes with time and location, that the universe is more interesting, more complex, more wonderful than our best theories suggest. We sent 2 spacecraft to the edge expecting confirmation. We received revelation. The spacecraft are dying now, the power fading, the transmitters falling silent. Soon there will be no more data, no more measurements, no more surprises from instruments that have functioned for half a century beyond their design life. But what they taught us remains. What they discovered persists. What they revealed about the universe and about our capacity to explore it cannot be taken back. Voyager showed us that we can build machines that survive the harshness of deep space for decades, that we can communicate across billions of miles, that we can answer questions about places so distant that light from the sun takes a full day to reach them. It showed us that the universe does not conform to our expectations, that every boundary we approach reveals new complexity, that every environment we encounter for the first time surprises us, and it showed us something deeper, something about who we are. We are a species that looks outward, that asks questions about what lies beyond the horizon, that builds machines to go where we cannot, that encodes messages on golden records and sends them into the cosmic ocean, knowing they will almost certainly never be found, but sending them anyway because the act of reaching out matters. The spacecraft will drift forever, silent ambassadors carrying the sounds and images of a world that existed for a brief moment under a star that will eventually fade. They will outlast our cities, our civilizations, possibly our species, and they will carry with them this truth. We were here, we wondered, we built these fragile machines and sent them farther than we ever thought possible. And they taught us that the edge, wherever we think it is always farther than we imagined, stranger than we predicted, and infinitely more beautiful than we dared to hope.